right, welcome everybody to episode 20 of the Playing Games podcast. And today we have a very special guest, Dr. Tony Blazevich. Dr. Blazevich, how are you doing today?
Really well. Good to be with you.
Thank you again for your time and being able to join us for an exciting podcast that many people have been looking forward to. Well, before we get started with anything, why don't we take some time so you can introduce yourself a little bit so people can get a little bit to know of your background and a bit of who you are, if that's all right.
Yeah, sure. So I was born and bred in Brisbane in Queensland and did an undergraduate in what we called human movement studies, which is basically sport and exercise sciences, and then did, I guess in the old days, what used to be a 1-year research degree that we called an honours degree. And then eventually, a year or two later, did my PhD. And I guess in my research in those early sort of honours PhD days was really around trying to understand how to use strength training or resistance training to improve speed and power in athletes. Because like a lot of us young ones, all we cared about was, winning Olympic gold medals and winning championships. And there were a lot of ideas around back in those days about velocity specificity of training and movement pattern specificity of training. So I was hoping, I guess, to find out more about how training at higher velocities might be beneficial for sport, or replicating movement patterns would be beneficial for sport. But interestingly, as I got into the research space, I guess I found out that a lot of things weren't as simple as they seemed, especially when you're already working with people who are doing multiple forms of training. And what those early days really taught me were two things about science. One is actually everything isn't always as it seems. It's usually more complex. And once you start testing outside of the normal space, you find things don't work the way we expect. So I started proving myself wrong from an early age, and I'm still proving myself wrong today. I think the second thing I kind of got onto was that it wasn't so much about whether one type of training is good, what we might call training specificity, but that there were maybe certain adaptations to different forms of training that could be beneficial or not beneficial, depending on the context and the person and where they're at in their life. And so I kind of already had this idea that we really need to understand the adaptations that we want to optimize performance, whether it's in a rehabilitation clinic or working with athletes or trying to get an elderly person to move more independently in the home. And then we needed to understand much better how the different forms of training and different ways we could train would then alter those adaptations. And that's where, I guess, once I'd finished my sort of postgraduate work and got into academia, I really started to head. I started to not only have the biomechanics, because I was a PhD in biomechanics and particularly focusing on muscles and tendons and nervous systems there, but I had to add a lot of neurophysiology to truly understand how the brain and the spinal cord was adapting, how important they were for explosive versus high force versus endurance type activities. And then once I had those skills, I was able to sort of layer the different areas on board. So we could go right from the brain to the spinal cord, to the muscles, to the tendons, and then also look at whole body movement. And once you can do that, you find out some really great things. And again, probably unfortunately, find out a lot of things weren't as they seem. And even today, there are lots of areas that I'm sure you've read about in my research where I'm kind of showing the opposite of what we expect, and that things might not always be as they seem.
Absolutely. And you are also very into performance in athletes, but also in hypertrophy as well, right? In muscle building
Well, yeah, kind of everything. I mean, again, when I was younger, I was lucky enough to work even through my honors and PhD with a lot of elite athlete organizations, a lot of youth development sport. So that sort of got me into it. I think I was a very keen athlete when I was young. So it's what I thought I would do. When I got my first job was at Brunel University in West London, and I was lucky enough there to be able to liaise with a lot of professional rugby and soccer or football organizations. At one point, I was the lead strength and conditioning coach for UK athletics, so I was lucky enough to work with the top 30 athletes across the UK in preparation for Olympic cycles, and work with the then new English Institute of Sport in a lot of coach education and S&C education and upskilling. So those early years were really about working in the athlete space, but being in the academic system where I actually had the time to think and the time to do research. Because as I'm sure some of your listeners know, when you're working with the athletes day in, day out, it really causes problems for upskilling knowledge because you just don't have time. So what we need is this wonderful hybrid, I guess, between people who have more time to think but aren't necessarily at the coalface, because we can learn from the coalface, and people who are at the coalface who then link with us because then they can work with us. And if I guess my utopia was that we'd all work together perfectly well. It doesn't always work that way, unfortunately, in some countries, but yeah, definitely that athlete stuff still comes through today, and I still enjoy today working with athletes whenever I get the chance.
And I think having that hybrid of knowledge is an application, I think, is very important, because there are many trainers and even strength and conditioning coaches who are still very behind on the research that we know today from like the 1990s, things that are now known to be not true, they still believe. And so there is this gap in knowledge because they're probably so busy to sit down and, look at the data, or, interact with people who are looking at the data, because those people are also very busy.
Yeah. And, a lot of people in academia are there because we love it. We were athletes, or we still like to work with athletes, or we were clinicians, a lot of physiotherapists who are doing, academia, for example, a bit like you'd expect your academics in a music degree to actually be musicians and play in bands and everything else, right? But it is a reasonable thing to say that academics are not in sport every day. And it is reasonable to say that even some academics were never in sport or clinic and therefore don't understand it. And we take that on board. And I think any academic or researcher who doesn't understand that what happens day to day in the coalface is often something we forget about, I think that's really important for us to know. Ipso facto, those people who are in industry, I think, and again, when I look into industry across the world, I would say that if there was one area that I would upskill, it's the fundamental knowledge, that there's a lack of that fundamental knowledge, which means it's very hard to assess new ideas and very easy to go along with the experts you think should know their stuff without you understanding that maybe they don't, and that you're going down the wrong route. And how we can get that new information out, that important fundamental information out, is maybe something that your listeners can write in about and we can discuss in the future.
And speaking of knowledge, I hope for this podcast episode to provide a big foundation of like how much bigger the picture is than what people see either on social media or reading blog posts and things like that. So I hope someone who has been in the field can come in and, fill in that gap a little bit, and really show, speaking from experience too, because there are many people nowadays on social media who just read a lot of data and paper and think that they're experts, when in reality there's like a whole new world behind that published paper, right? So
yeah. And just to be really clear here, even for the researchers in the field, we read a lot of papers and we assess those papers and we consider what those papers mean, and we put that information into the framework or the model in our mind of how things might work or must work. But the only way we can really determine whether we might be on the right track or not is to go and talk to lots of other researchers. So we have to have meetings with them. We have to meet them at conferences. So if you're in applied sport and you're trying to understand something at the fundamental level, and you do actually go out and read research, just be aware that even the best researchers on earth are never certain that when they read the papers, they're truly understanding what happened. And unless you're talking to the people who got the data and know how difficult the data were to get, or knew the problems they had getting the data, it's really hard to know how to weight that. So if you're not in the space all the time, actually, it's really difficult for you to determine those things. And that's why, again, I think this communication is really, really important.
And I think that's how you can kind of decipher an expert from someone who pretends to be an expert. Because from my experience, people, when I reach out to the actual professionals who do this for a living, they always give me a very uncertain answer. And I know they're not, many people may not be pleased with that because they want an official answer. They always get, well, maybe not, we don't know. But the people who pretend they're experts usually give a very dogmatic claim on how things actually work. And they're like, well, this has been seen hundreds of times. But, if you've never been in the actual lab or has never interacted and worked with other researchers, I think it's very hard to take their word for it. And just sitting back and doing papers on a computer.
Yeah, I agree. I'm either smart enough to know what I don't know, or I'm really dumb because there's lots of things I still don't know. And I'm surprised when people say they do. Maybe it's just me. I don't know.
Hopefully today we people get to see the complexity with eccentrics, and a very popular trend right now, well, at least it was, but I think it might come back, about training muscles at longer lengths. Now we're going to kind of go from eccentrics to that, which kind of they go hand in hand a little bit, I think. But starting with eccentrics, I'm sure people here already know different isotonic contractions, but if you want to go over that really quickly, I'm sure nobody would mind. But regardless, with an eccentric contraction, we always hear that we are stronger when we lower the weight. And I mean, people can go home and try this themselves. It's a lot easier to lower the weight. I'll say it's easier. I don't know if a lot easier. It's easier to lower the weight than it is to lift the weight. So maybe you know, or you might have an idea why, or are we for certain, or we for sure know, do we for sure know if any mechanism that can explain that?
When you say any mechanism, no, but there looks like there could be something like 6 different reasons why we are able to produce more force eccentrically. Just to start off, however, with why it feels easier eccentrically, one reason is because we're stronger, we don't have to produce as much force, and therefore something doesn't feel as effortful if we're not trying as hard to lower something versus having to lift it, where we, let's just say for now, we're less strong and therefore we have to work harder and we have to try harder. And so that perception of effort is very different. But also remember, from a neurologic point of view, that we seem to have more inhibition in the system. So there are more inhibitory, we're paying more attention to inhibitory signals coming into the spinal cord and then up into the supraspinal or brain centers in eccentric contractions. So we're not able to recruit as many motor units or at those higher firing frequencies as we would for the same force of concentric action. So something feels a bit lighter because we literally have less descending drive coming down. That's not why we're stronger, but just to remember that why it feels easier can be partly due to that neural drive. Because remember, the harder the supraspinal centers work, the more they send a mirror or a copy of that over to sensory areas. We perceive that effort. And that's one reason why we feel less effortful in an eccentric compared to concentric. But of course, one of the main reasons it feels easier is simply because we are, for want of a better word, stronger, I guess. For the same load, if the muscle is lengthening, there seems to be a few advantages there. I mean, the simple one that I guess way back in, 50 to 70 years ago when Huxley was developing his models, the easy one is that when you have a normal sort of myosin cross bridge or a myosin head interacting with an actin filament, the myosin attaches in some configuration. And let's say it goes through a sweep angle of something like 45 degrees. It gets to a very specific configuration at the end of its working stroke. And as your readers know, we need ATP to bind, to release the myosin head. But the myosin head also has to be in a certain configuration. I mean, if you have a lock or a protein on the actin that fits the myosin head nicely, like a lock and a key, at a certain configuration, that lock is easy to break, and at other configurations, it's not so easy. So there's some slack in that. You can detach at sort of slightly different angles, but ultimately it really helps to be at this angle if you want to unbind. Now, remember, it's not just a lock and a key, like a protein that has to have a certain shape and then a head that has to have a certain shape. There are also charges. Proteins have a negative charge at one end and a positive charge at the other, and like charges repel and opposite charges attract. And so the opposite charge can help attract the myosin into the actin. So you got these sort of two things going on here. Now imagine at the end of a concentric action, you're at this nice configuration where ATP combined, where the myosin can quite readily detach from actin and then go back into its next stroke, right? What happens in an eccentric contraction is the opposite. You're kind of getting this binding, right? Because calcium then allows the binding site to open, and through essentially random chance and aided by the attraction of dislike charges, myosin will then find its binding site in actin. But now the muscle goes the other way. First of all, you now are not in a configuration here where myosin wants to really unbind from the actin. So it's not as easy for this to happen even if ATP is present, which usually means we need a little bit of extra energy to dislodge it. And that energy can be given in the form of work or stretch. And so if you essentially pull on it, the work of the pull, the energy of the pull can detach it. A lot of people say, you know, forcible detachment, or it has to be ripped from actin, almost like that's the reason we get muscle damage. And of course, it's certainly not. It's probably better off just to think of it as energy, right? If you pull harder, there's more energy that will help it unbind. You're trying to get the positive and negative charges away from each other. It takes a lot more effort if you're not in that nice configuration. So what does that mean there's more force? Well, it means there's more force because on average, you're going to have more myosins that remain bound for a bit longer. And as you know, if you've got more myosins bound, you're going to have more force. And by the way, if the head is here, it's quite easy because proteins are a little bit extensible and flexible. It's pretty easy to pull. But once you get in this angle here, it's really hard to pull myosin. I mean, actin and myosin are a little bit extensible. That was only found out in 1994, which isn't that long ago. Hopefully most of your listeners were alive back then. But we now know, of course, that actin and myosin are slightly extensible. But once you sort of pull on it, it's really stiff. So if you're in this configuration, the muscle is stiffer and stronger than if it's in this configuration where it can move a bit. So there's two reasons just at the cross-bridge level why we might be stronger eccentrically. There's a third cross-bridge reason. Linari, who was in Lombardi's lab in Europe, they also had done, I think it was using X-ray diffraction, but I could be wrong there. Have you ever seen those, that in the textbook, there's always one myosin head, right? But have you ever seen those videos or whatever where there are two myosin heads? And have you ever seen the photo of myosin? It has a big long chain and it has two heads. We always forget that it has two heads, right? And what seems to be the case is that one head will bind, and then as we stretch, there is something about the energy of the stretch or the configuration of actin and myosin that tends to cause the second myosin head to bind. And that's going to then, of course, increase the number of bound cross bridges and increase the force. And because it can happen quite easily, it doesn't require much energy to do so. So it means you've got this quite economic way of increasing force. So that seems to be another way in which eccentric actions are stronger. But there are some really serious issues with these sort of three cross-bridge based mechanisms. I mean, first of all, it doesn't really account, if you do all the maths on the energies and stuff that smart people do, they realize the energy costs of eccentric exercise are different from the energy costs that are measured. But also, if you do all the mathematical modeling of all the chemistry here, you end up with forces that are not high enough, that it's not sufficient to explain it. And even back in Huxley's day, you know, he talked about the idea that there must be this other mechanism, maybe some elastic mechanism that helps generate these much greater forces eccentrically. And I think this is where the more recent data in the last sort of 10 up to maybe 20 years ago from Walter Herzog's lab and Nishikawa and others has really started to maybe fill in this picture. I would say the next thing we want to talk to is about titin, right? Titin is aptly named. It's the biggest protein that I think we know of in the animal kingdom, certainly in mammals. It's a huge protein, and it spans that Z band. You know, the sarcomeres have these Z bands at their ends, and the titin molecule binds from the Z band onto the myosin. So in your textbook, myosin always looks like it's floating free. Of course, it's not. It is anchored into the sarcomere, and it's anchored by titin. And titin's a really complicated molecule. It has some stiff bits, but it also has some elastic, well, I shouldn't call them elastic, compliant bits. So they stretch, they deform on force, and they are elastic, so they also come back after force is released. So you can imagine then that as you're trying to pull a sarcomere, you've got these passive elements of titin that as you stretch them further and further and further, they're resisting more and more and more because they're made of atoms, and that's what atoms do. Atoms have an optimum distance at which they like to sit in their molecule, and if you pull them any further than that distance, they actually resist that displacement by pulling back. That's where elasticity comes from. So as you're pulling on the titin, the molecules within titin are going further apart, so they resist you more and more. That's why if you stretch anything, it gets harder and harder to stretch. You need more force to stretch at a certain distance. So now you can imagine that if you've got a muscle that's lengthening, titin is getting pulled more and more, and therefore it's contributing to force. So there's 4 mechanisms, but the problem is that even that mechanism seems to provide only about 10 or 20% extra force. So what else is there? And I guess, if we think that the picture now is much more complete or almost complete, it's because we now understand that titin has a second really cool mechanism. That one of those mechanisms is that titin has calcium binding sites. It has a region called the N2K and another one called the PEVK. So you can look them up. They seem to have these calcium binding sites that not long ago didn't know they had. And one of the actions of the calcium is it stiffens the titin straight away, probably through folding of protein or something like this. The second thing it does, so here are 2 mechanisms in one, is it seems to allow it to bind actin. So now you can imagine that if you've got a long spring of titin, it's highly compliant. Anything that's shorter is much stiffer. The material is the same, so the material stretches as a similar amount, but just simply because it's shorter, if it stretched a certain percentage of its length, that's not as far. In other words, it doesn't stretch far when it's short. So you can imagine now that the long titin spring binds up onto the actin, and now it's much shorter, which means it's a lot stiffer. So now as you start to stretch the sarcomere, you've not only got a stiffer titin, but you've also got a shorter titin that makes it stiffer again. And in all the modeling, it appears as though the binding of the titin, so the stiffening of the titin and then the binding of the titin to actin almost completely explains the extra force, the reduction in energy cost, and even the fact that if you hold the muscle for a very long period of time, the force remains. And that's called residual force enhancement. Your readers will have heard about it, your listeners would have heard about it. And the reason why that's really, really important is this. You know how I said myosin binds to actin almost like by chance, that it has to have that electrical charge and, it had to obviously have the binding site available. Well, everything in biology is random because obviously at the fundamental atomic level, everything is random. And the closer you go to atomic level, in other words, the smaller things here are, so if you go right down into the molecular level of a titin, you're basically down to single atoms. Because their properties are so random, everything at the atomic level is random, which means you can have myosin that's bound to actin and for no reason at all, it will unbind. It's what we call a stochastic process. It's like a random variable in biology or in the universe. And so through this stochastic process, myosin might bind, it might unbind, it might be more likely to be bound under certain configurations, but it's never 100%. In fact, the best understanding we have is that in fully active isometric contractions, maybe only about 30 to 40% of all the myosins are actually bound. And that's because some are in their weakly bound state, some are cross-bridge cycling, some should be attached because it's isometric, but they just detach and recycle anyway. Lots of things are going on. Just think about it as the muscle is always fluid. It's never in its actual static state. Why is this important? Well, because if you stretch a muscle and hold it for long enough, by random chance, myosin heads are going to unbind and then want to rebind again with myosin. They're going to move from their strongly bound state to an unbound. And over time, force should drop quite remarkably. In fact, at some point, those cross bridges should even not be bound at all. But we still have force there. And that force makes sense if titin remains bound with actin and is also stiffer and shorter and therefore producing force all the time, no matter what happens to the cross bridges. The other thing you notice is that the extra force, if you go from a short muscle length to a moderate muscle length, you get about the same force enhancement, a bit different on the ascending and descending limbs, but it's not much different, as if you're on the descending limb. Or if you're at the optimum of the force length relation where you have lots and lots of actin myosin bound, you get about the same force rise. In other words, this extra force we get doesn't seem to depend on the number of cross bridges that could possibly bind, because at really short and really long lengths, you should have fewer myosin heads that can bind. And yet we get force enhancement anyway. So this kind of shows us that the titin is really a big key here, because it does its job regardless of the length of the sarcomere, because the length of the sarcomere might dictate the number of myosin heads that bind, but not what happens to titin within some reasonable amount. Of course, the titin is more stretched. And if you go from the ascending all the way to the descending limb, you'll see some differences. But ultimately, the mechanism works across the length of the sarcomere. And so I would say that our current understanding is that the really big key to eccentric strength, in addition to some of those cross-bridge factors, is the role of titin stiffening and its binding to actin. I would say there's one last thing, and particularly Kisa Ishikawa will be big on this one, is that it seems as though when actin and myosin move across each other, the titin does actually spiral very slightly. And it looks like if you had if titin is now bind to actin, like we just said, and then the titin rotates, it's going to pull actin on a bit more and stretch it even more. The mathematical or proportional effect of that, to be absolutely honest, I'm not really sure. But that could be our sixth and final mechanism that we currently understand could add to the force for no extra muscle energy cost, or not much energy cost, of why eccentrics might be stronger, is that twisting of titin because of the rotation of actin as the sarcomere changes length. So it's a complicated process why eccentrics are so strong. It's not down to one mechanism, unfortunately. And to be honest, who knows where these models will end up. But according at least to all the mathematical modeling, according to what we expect to see in nature, these mechanisms combined seem to pretty much give us what we think is the full story. So if there's anything to add to it, it may not be earth-shaking, but who knows where we'll be in 50 years' time.
So a lot of stuff there. And from just to make sure I was able to understand, if I could simplify it down, could we say that during eccentric, and I'm gonna make a little comment about titin, because I know there's some contention there, and I'm curious to hear your opinion on that. So with the actin and myosin cross bridging, so we could say that they attach more securely in a way during eccentrics, and there might be more cross bridges attaching due to the double myosin head, possibly, because it's sometimes hard to think about that, because if the H zone is getting long in the sarcomere, like how can there be more cross bridge attachments? And I know Herzog, when he used Huxley's model, he said that during eccentric contractions there could be a greater proportions of cross-bridge attachments, but also more force per cross-bridge attachment. However, that model wasn't necessarily made for eccentric contractions, from what I.
Well, could I just to clarify that, if Lombardi's group are correct and the data are pretty irrefutable, it's just whether this is the main mechanism. At the time, they're like, oh, this is why, but probably it's not the main reason why. You've got to remember that myosin, like I said, only about 30 to 40% of all the heads are attached, even at some optimum length under a maximal isometric contraction, right? So there are plenty of heads left to go. And that second head seems to be something that could attach. So for that reason, you can have more myosin heads. Even now, remember, you say stretch, but if you go from the ascending limb to the optimum length, you've got more opportunity for binding, right? It's only when you go from the optimum length on the descending limb that you start to get a reduction again in the number of cross bridges. But even then, if you have two heads that combine rather than one, you've got a massive increase in the number of heads available for binding, even though you might stretch a bit and lose a bit of distance. The second thing is you talked about is not only the number of heads, but the force per cross bridge. And that's what, when I talk about the fact that the angle of myosin is a big factor there, because when myosin's at 90 degrees, it can't resist rotation as much as when it's at, well, it's never quite this. I do that for dramatic effect. But even if it's sort of here, if you do the cosine of the angle, a lot more of the force, it's very hard to stretch myosin this way. It's much easier to extend it this way. Plus the fact that if the myosins aren't unbinding, you're having to pull them, they're generating more tension just prior to that release than in a concentric, where they haven't yet generated that tension because they more easily unbind. So there are reasons why you got more heads, but also reasons why each head is producing more force. And so that makes a lot of sense from what you were just saying then.
Oh, okay. All right. And speaking of more heads, could it also be possible that like the lattice space of the sarcomere decreases, probably increasing the probability of attachments occurring? Is that?
Yes. Now remember, just don't conflate extension of a sarcomere with it being stretched. This is really important, right? And it's going to be important for our future discussions on muscle length and stuff as well. If you have enough activation in a muscle that you can get the sarcomeres to go to a shorter length, and there are lots of myosins bound, and we do this, then what that does is pushes away the actin and the myosin filaments. That is part of what causes the bulging in your muscle when you have the biceps. Of course, in pennate muscle, the rotation of the fiber also contributes significantly to that bulging, right? So it's not the only thing. But the fiber itself will extend outwards slightly. First of all, by the way, that means the sarcomere is doing work. So some of the sarcomere force simply goes into pushing the sarcomere out, right? It doesn't all go into length change. The second thing to remember then is, and I think this is the point you were going to make, is that once actin and myosin are further apart, the likelihood, we said it's a stochastic process. It's kind of like, it's not quite random because of course it's got hydrostatic activation, but there's a lot of random nature. And so the further the myosin is, the less probability it has of finally binding because the forces are weaker to draw it in. So once you can, if you have the sarcomere at long length, I'm not going to use the word stretch for now. If you have it at long length, then of course what happens is as the fiber goes out, it shrinks in at its center. This pushes actin and myosin closer together, and therefore there's more likelihood that for the same number of open binding sites, so for the same amount of calcium, in other words, for the same amount of neural activation to the muscle, you can end up with more strongly bound myosins. And this is why under submaximal contractions, a lot of experiments, not all, but a lot of experiments show that there's more force at longer lengths for a certain amount of activation than at shorter lengths. Because if you haven't got really full activation in the muscle, not all the binding sites are available, then at longer length, where you've simply got more probability for binding, then of course you're going to get more force. And this is the same reason why a lot of researchers who study muscle will say classic PAP, proper classic post-activation potentiation, works at submaximal forces. And that's largely because at submaximal forces, you don't have all the binding sites open. And if you can activate the light chain of myosin to bend a head closer to actin, then you're more likely to get that attachment. So at submaximal levels of force, you just simply got an increased likelihood of binding if that light chain is phosphorylated, the regulatory light chain is phosphorylated. So all of these come back to the same idea, that if you can find a way to increase the likelihood of binding, then it's going to bind better and produce more force for whatever those conditions are.
I'm glad you brought up PAP, actually. I do want to get a little bit into that, not too much. But regarding a quick question with the myosin, when they're like this, do you think that because this pull has a greater mechanical advantage to pull the myosin head, just maybe because there's a moment arm there that's larger, that could be why it's harder than pulling it from here, maybe?
Why it's harder, yeah. So obviously when the external moment arm is larger, a given external force creates a bigger torque at the myosin. And remember, these are just proteins that are just deforming through energy. I like to think of it like if you had a piece of plastic and you got a lighter and you applied heat to it, notice that the plastic kind of curls up. That's because heat is deforming the protein. In other words, you're putting energy, heat energy, to deform the protein. Now, of course, myosins move all the time. They don't just deform like a plastic, but you can think of them the same way. You're breaking ATP to release an energy. There's like an explosion there that creates an energy that then deforms the protein, which is a kind of a nice analogy. And that's all it is. You're putting heat on and hoping that the protein deforms. It's not like the protein is an active motor that somehow generates this incredible force to push itself. It's simply a protein that is folding up. It's just deforming, and it can only do whatever work it can do as it deforms and folds. It's not a magic motor. And so, of course, if you've got a big force, it's only going to be able to do a little bit of, it's not going to be able to move it very well. And this is another reason why we have a force velocity relationship, right? Like the myosin motor can only generate a certain amount of force. Luckily, the head of myosin is so tiny. It's about 20 nanometers. I mean, there's not even worth talking about the width of a human hair when you get down to 20 nanometers. Think about it that if you got a DNA molecule, not in its length, but in its width, the width of that alpha helix, you know, of a DNA molecule. If you put 8 DNA molecules right beside each other, that's the whole myosin head, right? So it's very, very short. The neck region is much longer, and that might flex a lot more. The head is not, and the head moving like this is working under what you might call low gear. You know, it needs a lot of these to move anything. In fact, if your biceps shortened at the speed of a sarcomere, because a sarcomere has to have so many, because they're only moving, well, depending on under what conditions, 7 to 12 nanometers per cross-bridge cycle. Even at the fastest rate of a cross-bridge, it would take you 2 or 3 hours to flex your elbow, right? That's how slow sarcomeres work, because they're working under really, really low gear, because the myosin head that's moving is really, really short. So it is true that if you have the sarcomere in this configuration, it might apply slightly lower force than under this configuration. But it's more the point that in this case here, it is applying still a force and moving, and then it detaches. And once it detaches, it's no longer applying a force until it can do this. But it does have some compliance. So you're right, and that's why I was trying to explain to you that compliance affects force. And what it seems to do is not allow the myosin to actually go as far. So under light loads, it can go a little further, and under heavy loads, it doesn't go as far. Now, by the way, I just want to be really clear that once the myosin goes further and further, notice that your finger starts going upwards. In other words, for extra rotation, it's moving in this direction, not in this direction. So the more the myosin head rotates, the less effective it is at shortening. So while I say in this configuration it's weak, actually by the time you get to here, you don't really want to be attached anyway. You'd rather get back to here and be stronger, because you don't want to be lifting up, you want to be pushing. So it's not the main mechanism. But what I am saying is that when the myosin is like this and it doesn't detach as well, it requires more energy to detach. It's also the case that myosin is elongated and it's not stretching. So because it's so stiff, if it was locked here, it wouldn't be as stiff. But because it's locked here, it is stiffer. That's one reason why the myosin might actually produce a little bit more force. Yeah, because it can't even be stretched by the time it's broken off. Whereas here, theoretically, it could have been stretched a bit before it got broken off. Have I explained that a bit better?
Yeah, and I mean, it could be that these sarcomere arrangements, these sarcomeres are arranged to somewhat minimize speed, you could say.
Say that again. They're arranged what? Sorry?
To somewhat minimize speed.
Well, yeah. Effectively, they're good at producing force and not good at producing speed. You know, remember that when you jump or bounce on the ground, right, your calf muscles are probably producing something like 1,000 kilograms of force. I mean, it's hard to comprehend that something that weighs a kilo or less can produce 1,000 kilos of force. It does that because the myosin head is so small and because there are trillions of them. So you've got a muscle that essentially works in low gear, like a big truck trying to get a heavy load uphill. It's very good at producing force. It's just not very good at producing speed. We're highly limited by speed in the human muscle. In fact, all skeletal muscle, particularly mammalian. And so we have this force velocity relationship that isn't just a straight line. It's seriously curvilinear, going straight down it. You lose a slight increase in speed, massive loss. So there's no doubt that muscles are built for force and not for speed. But there's also no doubt that if you locked it here, it would be a bit more compliant and stretchy than if you lock it here. And that's all I'm saying. Because in fact, under very heavy loads, muscles are a little bit more efficient than you might have mathematically estimated. And it's because they get to about here, where they're still pulling horizontally, and then they detach and grab again. And because you're moving so slowly, this doesn't really affect it too much because the myosins are spending so long producing force that there's lots of them always activating. But if under light load conditions, they do tend to go further. And when they go a little bit further, they're actually pulling upwards. They're doing lateral work as much as linear work. So for the same amount of work, you're getting less actual distance. And so in fact, under really heavy load conditions, we're a little bit more efficient at the muscle, which is another reason maybe why we're so strong, but not so fast.
And I hope this kind of is able to allow people to comprehend why there could be so much going on during an eccentric contraction. Because usually you tell somebody that there's less neural drive or there's less activation or energy needed for an eccentric contraction, and then they might be, well, doesn't this binding of cross bridges require energy? But at the same time, you have situations like rigor mortis where all the ATP or all the cross bridges just bind without energy, which I think is really cool.
Yeah, and by the way, just to be really clear, you know how I said only about 30 or 40% of cross bridges are really attached even in a maximal isometric contraction, at least for 3 or 4 studies that I've read, that's about the average. It's certainly less than 50%. Go to rigor mortis. In rigor mortis, you can eventually get, if it all works well, 100%, right? Because again, stochastically, they're going to bind randomly at some point. And if there's no ATP available, they don't unbind. And so if you take a muscle with rigor mortis, it is a lot stiffer than your maximal isometric contraction. And that's a good reminder that even during maximal isometrics, you're nowhere near fully activated in the true sense of how many myosins are attached.
And before I get into titin, could it be that with all these different configurations happening, do you think that there's some friction occurring, and friction can work both ways? So maybe when you're doing an eccentric, friction could be working to aid you, or sorry.
It will help you because friction will resist the translation of the myofilaments. Yeah. So first of all, yeah, really good point. I mean, so there's friction at all levels of the muscle. This is called viscosity. You've probably heard that most biological tissues are viscoelastic, and viscosity is essentially the friction caused by solid elements that move over each other. But it's not just friction in the sense of, you know, sandpaper on wood where there's direct physical contact, because again, you've got positive and negative charges, for example. So as things are moving over each other and positive and negative charges are moving past each other, there's going to be slight increases and decreases in the amount of attraction between proteins and everything else. You've also got water. Now, if I'm to be really clear, water has a poroelastic effect typically in biological tissues, but it's wrapped up in viscoelasticity because, of course, water molecules have to flow and they are charged. And so as the water is moving, that affects the charge at actin and myosin. This is the suspected, or I don't want to say it's the proven reason, but it looks to be the reason why if you have your muscle cells a little bit swollen with water. So when you do a warm-up, you generate a few lactate ions if you warm up hard enough, and that will draw in some water into your cell, and your cell becomes stronger. Some forms of testosterone, a lot of what you call your androgenic steroids, for example, bind water in the muscle and increase water mass. And one reason that seems to increase the force of the muscle is because water then affects the attractive charge between actin and myosin, and it keeps myosin attached longer. So it means that your working stroke is a bit longer, and on average, your myosins will spend a bit more time attached than detached and recovering. And so even just water molecules in your muscle affect the way actin and myosin slide past each other. So it is very possible, of course, that if there is friction based on anything from electrical charge, the effects of water, or anything like this, that should cause a problem when you're actively shortening, because you have to do work to shorten against that friction. Whereas on lengthening, where there's an external force doing the work for you, you would then need less internal work to be done to resist it. The question so theoretically, absolutely, that makes a lot of sense. The question is how big that effect is relative to the effects of titin, which are to my understanding and to the modeling data and to all the knockout data. When you get rid of cross bridges and still look at the effects of titin, it seems to be massive. Both the stiffening of the titin and then its attachment to actin, that seems to be really, really huge. And so relative to that, plus then the effects at the cross bridge level itself, I would have to guess that the effects of friction are very, very minimal. It doesn't mean they're not there, but they'd have to be very, very small. Maybe if you get on some of these, cellular researchers or these molecular researchers who are using, gold tweezers to pull on them and doing a lot of the laser diffraction, they might be able to give you a much better understanding at that level of the muscle.
Well, that makes sense. And regarding titin, I mean, all this seems to be, titin is also known as an entropy spring, right?
Yeah, well, I mean, pretty much most are, right? Because entropy means progression towards disorganization, and all molecules that we know of resist deformation into disorganization because every atomic bond has an optimum distance that minimizes the energy, right? Just really, really quickly, if you got two molecules and they're a long way away from each other, just like if you imagine being high above the Earth, and the Earth, if the higher you are, the faster you could fall, the more potential energy you have. You remember that from school? Well, if you have atoms that are a long way away, they might have a lot of potential energy. But of course, these things are also moving, so they have kinetic energy. And when you have a bond form, it's when you've got electrons flying around a nucleus of one atom, and they come close to the electrons in another atom. But these electrons on this atom sometimes are coming so close to the positive charge of this atom that there's an attraction. So there's potential energy between the electron of this atom and actually this nucleus over here, and they come closer and closer. The problem is with an atom is that the how does it work? The closer the electron is, the faster it spins. So it has more kinetic energy, but it's closer, so it has less potential energy. So now you have two clouds of electrons coming together. They've got both a potential energy to this nucleus, and as they come close, they've also got a potential energy to this one. Of course, they've got their kinetic energies, and at some point, those atoms are at a specific distance where, on average, all the kinetic energies plus all of those potential energies, all the distances, are least. Now, if you move them closer again, not only do the two positive charges want to repel, so they don't want to be near, but actually you end up with an increase in the total energy of the electron pool as well. And so these atoms don't want to come closer together than that, right? That's what we call the ground state in this chemical bond. Now, if you try and pull them back apart, the energy goes up again. And that means to get to their naturally lowest energy state, they'll want to come back together. So pretty much, well, I'm not a physicist or a chemist, but I would say every structure on Earth, because it's made of molecules, will have this entropic bond in that as you try to pull things apart into disorder, they'll want to come back to their ground state, which is order. Now, this is very different because you're talking about, almost instantaneous chemistry here. This is very different from the fact that the whole universe is progressing towards increasing entropy, right? It's getting more disordered and it's losing energy, right? That's different from I am right now trying to stretch this protein or this molecule.
That makes, I hope people don't underestimate the importance of basic chemistry and physiology and physics that we learned in high school, because they tend to overlook that, and they don't really think about that when we talk about skeletal muscles and what we'll get into in the future. But having a solid foundation of all these basic principles seems to be very important from all the points that you brought.
Yeah, it's really unique.
Now, regarding titin, before we get into hypertrophy, there is some contention that titin, I don't think anyone has measured the forces in titin that are compared or near the forces measured in muscle. And when I spoke about this with Dr. Lieber, he seems to be very skeptical on the role of titin, because what they find is that the extracellular matrix seems to bear more of the passive, seems to have more load bearing with passive tension. And so one question that brings up that comes to my mind is, well, if the extracellular matrix does indeed bear more load than titin, because maybe if we zoom out from the muscle level, or to a smaller level, to a more macro level of the muscle, maybe titin's role, is it still that large? And could it be that the ECM plays more of a role in helping with that eccentric force because of some fluid shifts going on or anything like that? Or do you think the ECM doesn't really help with eccentric force at all?
I'll say you're right and wrong at the same. So the ECM probably only plays a minor role in eccentric contraction, but it plays the majority role in passive tension. So what seems to be happening here is you're conflating two different states of muscle. So what Rick Liebel will show, and his research team have shown, and I completely accept the data. So if you go right back to a single muscle fiber, or even a myofibril within the muscle fiber, let's just start with the muscle fiber. When you have a muscle fiber and whoops, I'm just trying to,
if you go right back to a single muscle fiber.
I'm trying to quieten my phone down and it's just talk to me. I was like, well, if someone rings my phone right now and then I've pressed Siri and it says single muscle fiber. All right, so let's go back to a single muscle fiber and you're stretching it passively. In the single muscle fiber, you've basically got rows of sarcomeres. You don't really have an extracellular matrix, especially if you've chemically denatured it, but either way, even if you pull that cell out and it's still got some extracellular matrix sitting around it, it's not bound to anything. It's not very effective. So now if you pull on it passively, given that most of the cross bridges are going to be easily detached, and because it's an inactive fiber, very few are going to be attached at any point anyway, the majority of the passive tension is due to titin. So in a single muscle fiber, I think it's been very clearly shown, and I accept the data, that the majority of the passive stiffness of a sarcomere or a fiber resides in titin, and that if we change the titin, if we influence the titin, we get a big effect. The problem is a muscle is not a big muscle fiber. And this is really important for lots of different things, from the inertia of the muscle and how much work it costs. If you've got big muscles, it actually increases the ability, the cost of a muscle contraction compared to someone with small muscle fibers. It also massively changes its passive properties, because if you now have a complex muscle rather than just a big muscle fiber, you now need to connect all the fibers. So if you just had a big muscle fiber, it would still be that titin was the most important thing, even though it's a 1 kilo muscle fiber. But in a muscle, you don't have a 1 kilo muscle fiber. You still have tiny fibers, and you need lots and lots of them to build your muscle. In fact, you not only have lots of muscle fibers, but they are also grouped into fascicles. It appears as though, and researchers like Guy Dosick and stuff who do much more of this than me, they will argue that between the fibers, you have an extracellular matrix. We have the wrapping around the fiber that we typically call the endomysium. Those endomysia actually are reasonably poor at sliding on each other. So what happens if we try and pull a bundle of muscle fibers? We're not even talking about an entire fascicle's worth. You just get a bundle of muscle fibers and pull them. It turns out the extracellular matrix is quite stiff in this direction at the endomysial level. So compared to titin, which is also playing a role in the fiber bundle, let's just throw out an average that maybe 60 or even 70% of the resistance of the fiber bundle now comes from the extracellular matrix. And a smaller proportion, let's say 30-ish%, comes from titin. Now let's go all the way up to building up these bundles of muscle fibers into fascicles. And around a fascicle, you have the perimysium. Now it looks like the perimysium is very stiff laterally, but actually a lot more, I guess, compliant. So the extracellular matrix at this level has lots of cross bridges that are actually easier to slide. And this is really important because when you have muscles that are pennate, as they shorten, the fibers rotate. And to do that, you actually need some slip between the fascicles. It looks like most of this slip occurs at the fascicle level. So at the fascicle level, it seems like the ECM is a little bit more compliant in the longitudinal direction. So it doesn't add a huge amount, but it's still adding a little bit more. So once you now go up to this level, now all of a sudden you've got the endomysium and the perimysium, which now add up even more compared to titin. But let's go to a whole muscle. You now have the epimysium and the fascia. They are a lot stiffer in elongation, as well as, by the way, in radial, but that adds even more to the stiffness of the muscle. Now, let's remember that a muscle is almost an incompressible fluid. Those of you who've done a set of heavy bench press or run a 400 meters knows that the muscle then swells because it generates byproducts. Particularly lactate seems to be quite potent as an osmotic gradient. So it draws water in. It's not just blood flow. Water flows into your cell. And as water flows into your cell, it distends it outwards. Now, if you distend something outwards and then try and pull it, it resists because you have to do enough work, not just to stretch it, but that work has to also compress it in its cross section. And when you have lots more water and you distend it out like a full balloon, you have to do a lot more work to compress it. In other words, it's stiffer. So now by the time you add up the endomysium, the perimysium, the epimysium, and the effects of water, all of a sudden at the whole muscle level, the effect of titin is tiny. You know, it'll vary depending on architecture and muscle size and the specific types of titin you have, your genes. But if it was less than 10%, 5%, you know, I wouldn't be surprised. So yes, at the whole muscle level, your passive stiffness has much less to do with titin and a lot more to do with the extracellular matrix. That's not an eccentric active contraction. Because as you know, when you do an isometric contraction and then try and stretch that muscle, the effect of the contraction far outweighs any effect of the passive. If I was to stretch your plantar flexors passively, force goes up. If I said now do an isometric contraction, force is already up here, and then we stretch it even further, I think all of your listeners will know, it makes a lot of sense that once the muscle is active, the force far exceeds the passive force. So now what affects muscle stiffness in elongation or eccentric strength in an active condition is now not only not the actual stretch of passive titin, it's got to be to do with the stretch of the cross bridges and any other active component. And remember, if we go right back to the start, we said that once we activate muscle, it turns out that titin does seem to have these calcium binding sites. And it's the binding of the calcium in active contraction that not only stiffens the titin, adding potentially 10 or 20% stiffness, but also then seems to cause it to bind to actin. I'm not 100% sure exactly how much of it's the stretch, how much of it's the calcium. I'll have to go back to the papers. But once we have once we have titin actively bound onto actin, which only happens in active contraction, you now have a whole different configuration. So active eccentric is different from passive stretch. And I think that's where the conflation was happening there. Does that make sense?
Yeah, I think that really much clears up because I was one of the people that used to think that during eccentric contractions, the extracellular matrix would play more of a role because it has these paramecium cables and all these other things. And I think there was that distinction that needed to be made. So I will say I did misunderstand that.
Yep. Can I just really quickly say, though, that when we talk about muscle damage, you know, a DOMS, and I think you wanted to ask about that at some point, remember, it looks like your extracellular matrix, whether it's the non-collagenous parts like Desmond and my brain's all of a sudden lost me, even though we study this damn molecule, integrins. The integrins and Desmond probably play a really key role in how the fiber elongates during active stretch. And same with potentially the collagenous extracellular matrix, which is what you're normally thinking of with an extracellular matrix. That seems to play a key role in how the fiber membrane stretches and whether stretch activated channels on the membrane then open. Because remember, you've got calcium sitting outside the cell as well as being flooded into the cell. Remember, the cell is a muscle fiber is a cell. And so when the stretch activated channels open, you get an influx of extra calcium, and it looks like it's that extra calcium that then triggers the beginning of the degradation process that we often call muscle damage, which isn't really I guess a damage or a ripping or a tearing of the fiber, but it starts that breakdown process and the loss of force you get with eccentric damage, and eventually triggers the pain at a later date. So it is true that the extracellular matrix, not necessarily always the collagenous part of it, but even the non-collagenous part of it, does play a role in how the muscle fiber stretches, even during an active contraction, because that then affects how those stretch activated channels, the sacs, open to allow extracellular calcium, and that affects damage. And probably the best, I guess, hypothesis at the moment for why we have such a rapid repeated bout effect is that in very, very rapid time, within hours, certainly within 24 hours, we can, particularly the non-collagenous extracellular matrix adapts so rapidly that next time you actively stretch it, those stretch activated channels are less active, less calcium flows in, and you have less damage. So you have this repeated bout effect, which is probably related to the extracellular matrix.
Well, speaking of muscle damage, now that we're here, I hope now people have a really strong understanding of eccentrics, because that builds a foundation where we get the ball rolling now on everything. Because so now there's this, there's these changes in configuration of the myosin heads and all that stuff that could put them in a better advantage. And with eccentrics, the ECM maybe plays a role, but titin could be more important in active eccentrics rather than passive, from what I understood. And with damage, now there is this also controversy that eccentrics don't build as much muscle as concentrics because of two reasons. One, they hypothesize that there's less motor unit recruitment, although I'd like to say that there's less firing rates, but I think the recruitment is similar. And two, because eccentrics cause damage, it kind of like offsets that benefit of eccentric contractions if there is a benefit. Now, I don't know on the research if eccentrics are more hypertrophic, because there is that discrepancy of, are you really comparing concentrics to eccentrics? Mm-hmm. And if you are, there is that eccentric overload that isn't the same as the eccentric that we will see in the gym.
Okay, yeah, look, a really, really complicated story. And I will argue that I don't think we yet know the full story. So I'll just give you maybe an idea of where I'm currently sitting based on the evidence that I've seen and the people I've talked to who study this a little bit more detail than I do. So first of all, if you just read a whole bunch of meta-analyses, you'll find as many meta-analyses that show that eccentric training leads to more hypertrophy than concentric, as you'll find meta-analyses that show there's no difference. And that largely comes down to which studies you include or don't include in the meta-analysis, and whether those studies were done well, whether there might have been bias in any of those studies. And it gets really difficult. And this is one big problem with us relying on meta-analyses, is that, it's not just crap in equals crap out, but there are so many nuances and differences to how people run their studies, how they measure them. Remembering things like DEXA, in my opinion, cause lots of problems, because DEXA is so influenced by fluid content that if you've got a type of training that might increase fluid versus decrease fluid, you'll get a completely different lean mass. Remember, they're not measuring muscle, they're measuring lean mass. And we can just take some creatine and get a completely different result in DEXA. So, do you include only MRI studies? Do you include ultrasound cross-sectional area for thickness, where if you get the thickness in the wrong direction, you don't see the change in thickness, even if the muscle got bigger? There are huge numbers of issues that I would see across the literature. So I really struggle with some of the meta-analytic outputs, just because it will be so sensitive to the studies you put in, how they were done, and particularly how they're measured. With that caveat, what I would argue is reasonably well shown is that under very light loads, so let's say you go for a walk, the loads are very light. If you walk downhill, the loads are slightly bigger. We have a bit more collision of the foot on the ground, so we have vibrational loading, but we also have a bit of eccentric contraction in the muscle, because the muscle will actually lengthen. Compared to uphill, where you work a little bit harder, the muscles are working concentrically. Now, there are studies, particularly if they're in younger people, they often have to put a backpack of load on. In elderly, I think there's at least one study with no load. where they find some reasonable hypertrophy in the muscle under light loads. And I would argue that I'm unaware of a study under light loads in concentric that can do it. And when I say light loads, I'm talking about walking. I'm not talking about these 30 RM to failure type studies where there's still reasonable load and we would maybe still put it under the configuration of strength training or resistance training. So under very low load conditions, based on the current evidence, I would argue that eccentric training is more likely to give a hypertrophic response. And one reason might be that it does allow more calcium into the cell through those stretch activated channels, because ultimately, if you're going to build protein, you need a calcium signal. And the reason why we talk about firing rates and activation and all this sort of stuff is simply because if you had activation, you had calcium. Calcium signals to the genome, tells the genome to do stuff. And so without calcium, you've got nothing. The problem with hypertrophy is it doesn't seem to be just as simple as calcium, though. For example, we have local growth factors, the most famous being MGF, mechanogrowth factor, which is a version of IGF, of course, and it works within the muscle itself or within the muscles around it to selectively cause hypertrophy of a muscle, right? You've also got what looks like some evidence directly of a mechanical transduction, potentially through titin, that when you have this specific mechanotransduction, we seem to get hypertrophy. That's probably important because just having calcium could trigger lots of things in the cell. For example, if we have lots of low-level calcium in the cell, we might shift towards slower fiber types because we get, which one is it? The translocation of NFAT into the cell. And that's because calcineurin, who some of your readers may have heard of, gets upregulated if there's lots of calcium for a long time. And that causes NFAT to translocate. And that seems to increase the amount of slow twitch myosins you build. Having lots of calcium there might increase some of the metabolic signaling through that RAS, RAF, MEC, ERK sort of energy signaling. So the question is, we say calcium matters, but the question is, what is the calcium going to do? It could be that when we get proper mechanotransduction, that is when we get some sort of proper load, then the calcium is more likely to stimulate protein synthesis rather than just upregulate, say, energy or directly do slower twitch fibers. As you know, heavyweight training, you're more likely to get fast myosin built, not slow myosin built, right? And so it looks like mechanotransduction either is important for hypertrophy or at least has to work with the calcium to tell the cell that that calcium in big spikes actually means build proteins, please. So now you've got calcium, you've got mechanotransduction, you've got local growth factors, but what about fluid? In almost every cell, not just muscle cells, osmotic fluid shifts increase protein synthesis in cells. Something about fluid stress, they call it stress, but maybe it's a positive signal, causes cells to get bigger. So maybe that's one of the reasons, for example, why when we train a bit to fatigue, which draws lots of water into our muscle cells, we get a bit of hypertrophy. Having said that, we always debate whether that's just an increase in sarcoplasmic volume, which would be required if you have a lot of fatiguing contractions because you need a lot more calcium, which means you're going to get more water sitting in the SR. So the sarcoplasmic reticulum will expand a bit if you do a lot of fatiguing work. But also it seems like if you do some fatigue and you get more water mass, maybe that's also triggering some hypertrophy of true protein structures. This is where it all gets so confusing that I'm not aware of any paper that pulls apart the specific and relative importances of all these different mechanisms. What I will say is I think they're all important because it's good to have redundancy in the system. I mean, if you've got to lift really heavy loads, it would really help to get some hypertrophy so you've got more motors to lift the heavy loads. You could imagine that just mechanotransduction with some high spiking calcium signals with lots of rest so you only get the big spikes might do that. Alternatively, you might have a lot of eccentric training where you might think, oh, the muscle might get damaged and injured, so wouldn't it be nice if the muscle was a bit bigger? Because the bigger the cross section, the lower is the muscle stress, which means the muscle should survive injury better. So that might be good. So something about eccentric action on titin might signal to get a bit more hypertrophy to help stop that. But even if we're just doing lots and lots of metabolic work, I mean, have you noticed that marathon runners and 10,000 meter runners are really lean, like because low inertia is low body mass is really important. But if you look at your ultra trail runners who run slower, so inertia is not a bigger problem, but have so much muscle damaging impact that they seem to have more hypertrophy in their muscles. They tend to be bigger people than, and you think the longer you run, the thinner you'd have to be, but actually it's not the same. So there seems to be that, or even cyclists, you know, who don't do any weight training, maybe they do end up having a little bit more muscle mass than a non-cyclist. So it's even something about endurance training that causes the muscle fibers to hypertrophy, maybe in this case more the slow twitch fibers, but they're still hypertrophying. So maybe fatigue in some way has to be a signal, because again, that allows more metabolic action, it allows more storage of fats and glucose, it allows you to cycle through more motor units in a submaximal contraction. Remember, once a motor unit gets a little bit fatigued, it'll slow down its firing and others will pop in. It would be really helpful to have some hypertrophy, to have bigger, more resilient fibers. So there's lots of reason we might need hypertrophy, and therefore it makes sense we have redundant mechanisms. We have multiple mechanisms by which hypertrophy could be optimized or maximized or improved or triggered maybe. So it also makes sense when we go, oh, in the gym, if you just do a bit of heavy stuff and then a bit of fatiguing stuff and then a bit of eccentrics, it all seems to work. And every time we shift, we get a bit of an improvement. That's probably because what we're doing is we're simply hitting different mechanisms in different ways. We're hitting different signaling processing pathways in different ways. And we're hitting all the different triggers that might trigger some hypertrophy. So when I come and look at muscle like that, like it makes sense to me that a biological material will have this redundancy in the ways at which it can generate hypertrophy, because it might need them for different reasons. It makes sense then that maybe under some conditions, eccentric could trigger more hypertrophy because of the mechanotransduction. It triggers activation of titin better, which seems to be an important mechanotransductive material to the genome. We have an influx of calcium from stretch-activated channels, and calcium amplitude seems to trigger signaling in the cell. But at the same time, we also end up with a repeated bout effect where we're probably not getting the big calcium signal. And it might be that we just need more activation. So going a bit more towards fatigue, where sure, you still have a big enough spike to say, hey, this is for hypertrophy, not for energy, but you have a few more of them to really give a chance for that hypertrophy to occur. So now you're thinking maybe concentric could be good because of the fatiguing aspects. So once we get to these high level, bigger force contractions, if I'm to be honest, I'm not convinced either way that either concentric or eccentric is better. It might be more to do with which signals has your muscle seen more recently, and if you switch the signal to a different signal, can you get an extra response? And this might be why when you look at meta-analyses for really heavy sort of what we might call proper strength training, a lot of them don't show much of a difference between concentric and eccentric, even though eccentrics can give you a bigger force. And if mechanotransduction is key, that should give you more hypertrophy. Concentric, you might have more fibers active with more osmotic fluid shift and more calcium signal. And in the end, I don't know. So this is one of those ones we talked about at the start. I will tell you that I'm not actually sure. I don't know yet that I can say that one is better than the other. And I think it might be because the complexity of the signal is so great that it will depend on which stimulus you're giving now relative to which stimuli you've seen more recently as to whether it's going to be effective for you. And that's maybe my, I guess, hypothesis to test in the next 10 years if anyone wants to go and do it.
Oh, it's definitely an interest of mine, if I ever go for my PhD, to go more into that. And I think you also have, you know, I don't know if there's any data, but it could be that maybe the ECM may help in mechanotransduction, even though there's no mechanosensors that we know of, but maybe like a confusion in amino acids that it takes up. I don't know.
Well,
and
there must be something. There must be something. And again, I'm not 100% sure now of the full downstream target. You'd need to talk to someone who literally spends their entire world in the molecular realm, right? Which is not me. But for example, we have done work here on integrins, and particularly the effect of eccentric training on integrins, knowing that in animal studies, So the integrins, by the way, help take the force from the sarcomere to the extracellular matrix. So they kind of poke through and they help, they're part of the extracellular matrix, but they help to link the inside of the cell with the outside of the cell. And what has been shown, for example, is that if you take animals that have more integrins, so a more developed non-collagenous extracellular matrix, and give them a signal, they get more hypertrophy. And the belief is that signaling to the extracellular matrix is really important, or that the stretch and the forces on the extracellular matrix are then creating a signal back into the genome. Remembering that when muscles lengthen and shorten, you've got to remember they're not just longitudinal. I think this is one of the biggest problems in sports science as far as how injuries occur. We just keep thinking muscles do this. Muscle strain injury is because we stretch the muscle and it gets injured. And that's because sometime in the past, they got an animal muscle and activated it, stretched it, and it got injured. Well, no kidding. But that's probably not what's happening in humans when we move and get muscle injury, right? If you got to remember that as a muscle lengthens and shortens, it's also changing its girth, which means at the surface, you're also getting changes in this direction, in the radial direction. So you're not just getting longitudinal stretch and relaxation, you're getting a lateral stretching and elongation. And it could be that that's causing a lot of signaling in the genome that we're not even aware of. And that as this is happening, as you're stretching it, you need that extracellular matrix to adapt because you're actually doing work on the extracellular matrix. So you want the matrix to be a bit more compliant in that sense so that it stretches easier, so you're not wasting muscle mechanical work. But also, if you are doing lots of work, it kind of makes sense then. If you're always working at low forces, or, you know, and you don't need a lot of stretch, but once the force gets big, your tendon stretches, the muscle tends to get shorter, all of a sudden your extracellular matrix has to stretch further to accompany the big diameter. Maybe that is a useful signal to say, hey, I'm always stretching. That must mean you're generating these big forces. Can you please, you know, you might need to get a bit bigger here or something. I don't know. I mean, I literally, that's at the end of the limit of my knowledge.
I mean, and, you know, I know there's some good work from Dr. Perslow on mechanotransduction with like passive elements. I think he believes that titin maybe not even occur with the mechanotransduction similar to the others, something different there, and may not even need to signal like some sort of mechanotransduction. A lot of interesting stuff, and kind of goes to show that if you have somebody on social media saying that they know how things work, I think that's likely not the case. And then fatigue, I like to think that maybe with lighter loads, fatigue becomes an important signal because we need that reduction in force loss with metabolites or anything to therefore recruit more motor units. But then when you have high loads, maybe fatigue isn't that much of an important signal. That's how
and it could be fiber type specific, right? I mean, if you just do really heavy weight training, it does look like the higher threshold motor units, typically they're the faster twitch, do seem to be a bit more amenable to hypertrophy. Whereas, of course, with endurance training, you take a biopsy of a lifelong endurance trainer, their type 1 fibers, their lower threshold fibers do seem to have more hypertrophy. So it looks like there's multiple ways to trigger it in the muscle, and it might even then be fiber type dependent as well. So we've got to remember that, right? It's like, what do you want? And if you're a bodybuilder, you want both. So if you're a bodybuilder, you've got to find a way to get the slow twitch fibers to respond and the fast twitch. Whereas if you're a sprinter, you probably don't want slow twitch to respond at all. You know, you really just want the fast twitch, and you want to transition if you can. So you're doing as little as possible, but you still want a little bit of hypertrophy, at least in some of the work generating muscles like the hip flexors and the hip extensors, right?
And I mean, I think if you're building muscle, a lot of people think that slow twitch fibers don't matter. But I remember I was at a conference with, I'm sure you're familiar with Dr. Sue Bodine. Mm-hmm. She actually says that depending on the muscle, the slower twitch fibers could actually be bigger than the fast twitch. And there is this.
Well, and this is what I was just saying. Some of the slow twitch fibers can be bigger, especially, you know, it can be genetic. It can be in some muscles in the body, but even with training. I mean, if you do endurance training, we can see type 1 fibers might selectively hypertrophy.
Yeah, because
the other thing to remember is two things, right? First of all, in human movement or in animal movement, the faster we move, we think that the muscles always move faster. And that's only the case in what we might call work-generating muscles, like your hip extensors and flexors in running. In other muscles, that may not be the case. For example, in the plantar flexors, they tend to change length very little if you're already a well-accustomed runner or jumper or whatever, because it helps to remain nearly isometric. And in fact, there's often no eccentric at all. And if anything, there's only a little bit of concentric as you try and get a little bit of extra work out of that system. Now, if you're a sprinter or a jumper, yes, it does help if you have faster twitch fibers, because the shortening velocity of the whole muscle tendon unit is quite fast. And so if you've only got a limited time for force, the faster you can generate force, the better. So fast twitch, remember we call them fast twitch because they can develop force fast, not necessarily because of their shortening speed. Shortening speed is more affected by sarcomere number in series, so the length of the fiber. Before we recorded today, you were talking about Tom Burkholder, who in a 1992 paper showed really nicely, in fact, very little association at all between fiber type and shortening speed of the fiber. And that's because when we normally see people do studies on shortening speed and fiber type, they normalize everything to the length of the fiber. They normalize it to the length of the fiber because they're trying to say, hey, do faster twitch myosins actually increase the speed at which sarcomeres can shorten? And because we know that the length of the fiber is the primary determinant of its speed, you have to normalize for that just to say, hey, at the sarcomere level, what's happening? Of course, in an animal, fiber length matters. So you can't just normalize to fiber length and say, look, fast twitch fibers shorten faster. You've got to look at the fiber length. Now, it turns out that if you think about this, if you generate low forces, the tendon, the distal tendon doesn't stretch far, okay? Which means that the muscle is often at a relatively long length. As force increases, the tendons stretch, which means the muscle shortens. Now, we'll get onto this in a minute, I'm sure, but it looks to us, and it looks to a lot of people, like the primary signal that influences the length of your fibers, other than genetics, of course, because muscles are built the way they're built. But the difference in fiber length, or the change in fiber length over time, seems to be dictated by the length at which it produces its force. If that's the primary stimulus, and since fast twitch fibers are often activated once force levels are higher, and therefore the muscle is shorter, you would expect fast twitch fibers to be shorter than slow twitch fibers. Yet, if fiber length is the primary determinant of shortening speed, doesn't that mean that slow twitch fibers should be faster than fast twitch fibers? At the very least, because the sarcomere shortening speed of a fast twitch fiber is faster, maybe it all balances out. And what you end up is, actually in vivo, there's no speed difference between fast twitch, which have faster sarcomeres but a shorter fiber, and slow twitch, which have slower sarcomeres but longer fibers. And that 1992 Tom Burkholder paper, I think it was in the rat, showing no relationship at all between fiber type and shortening speed, and that fiber length was the primary determinant, matches that theory really well. And there was a study by, his name starts with B, he was in David Morgan's lab, and I think what they tried to do was selectively activate within the nerve fast twitch and slow twitch fibers. And of course, they found that the primary determinant of shortening speed, and I think they even showed injury susceptibility, was actually the fiber length. And that one reason why fast twitch fibers get damaged more is actually just because they're a bit shorter, that they're getting stretched further in an eccentric contraction, and therefore more calcium influx, therefore more damage. And so lots of things that we see make sense in the fact that fast twitch fibers might be on average a bit shorter in many muscles, not every muscle. You need a tendon, right? You need the muscle to be able to shorten lots. Than slow twitch fibers, which slow twitch fibers can be fast, or as fast as fast twitch fibers. And if in a lot of muscles you're not getting a lot of length change, then it does mean that the slow twitch fibers are probably doing just as much as the fast twitch fibers to do work or to help you move. So this idea that if you move fast, you really only want fast twitch fibers and not slow is probably an oversimplification of what's going on. Regardless, we probably need a fast rate of force development if you don't have much time, because it's the time it takes to get to force that is the primary limitation of the amount of work the muscle can do, force times distance. And that's where neural activation rates and changing not only the myosin heavy chain to a faster myosin, but changing the series elastic slack to be stiffer, changing the non-actin myosin filaments, which also affect the speed of a muscle, like tropomyosin and troponin isoforms. Lots of things seem to affect how fast we can develop force other than fiber type in vivo in reality. And so it gets really, really dangerous just to talk about fast and slow twitch from that perspective.
Yeah, I think that can absolutely be a completely different podcast, because I know there's a lot of debate with like if slow twitch can really turn into fast twitch, or if it's the only transition is like between the fast twitch fibers and the slow twitch don't turn into fast twitch because the body's kind of lazy, so they want to like minimize force output or something like that. So like it wants to
minimizes energy expenditure. It doesn't want to have to rebuild a whole new, fiber type if it doesn't need to. But I mean, obviously we've got the genes to do it, right? If you're just switching genes on and genes off. So theoretically it can do it. It just seems to be in adults, and particularly in adult humans, it seems to be a really difficult signal to give, right? But over many, many years in say spinal cord injury, you do see the transition. So clearly it can occur. It's just that once you're a fully grown adult, it just seems to be a really difficult nut to crack. So if you're doing a 12-week training study, which seems pretty long, 3 months, you'll see between the fast twitch fiber types, you'll see it. And some of the hybrid fibers might tend towards a type 1 or something, but you don't tend to see the big jump between 1 and 2. And some people say it just doesn't happen. And I would argue, well, it certainly can. There's no reason it can't. It's just that it seems to be that the signal required is massive and long term. So you need years of training as an adult. I think there are, and it's not my major area, but they follow twins. And in twin studies where one twin does a lot of exercise from childhood and the other one does no exercise or different exercise from childhood, in those you start to see these really quite significant fiber type differences. And that shows that even though they had the same genetics, the different training probably is the main reason they ended up with such different phenotypes in their muscles. And so that suggests that maybe from childhood we can have a bigger influence, but once we're adults, it seems to be a really tough nut to crack.
Yeah, it seems easier to transition the type 2 to type 1 than type 1 to type 2, right?
Yeah, or 2X to 2B to 2A, not so hard. Type between 1 and 2 seems to be really, really difficult. Yeah, but what you can do is obviously selectively hypertrophy a type a little bit easier. Speed and power training and heavy strength training seem to maybe hypertrophy the faster twitch fibers much more robustly, whereas long-term endurance training might seem to do the same in type 1. And I'll also add here, and I'm not the expert, that there seems to also be a biological sex effect here, I think, with type 1 being more amenable to hypertrophy in females. Please check that with an expert. I don't want to be cited as being wrong. I haven't kept up with that one because, to be honest, hypertrophy is not my number one area of science.
But I mean, I will say that I know there is data with like building or using like lighter loads with heavier loads. There's like, you can't really like train fiber types. I've seen some stuff on that. I don't know if that's because like some limitations within that range. Maybe it's not a big enough range to create such a signal.
Maybe, yeah, maybe.
But with that being said, with eccentrics, I think that helps clarify like whether eccentrics grow more type 1 or type 2. But the growth from eccentrics, I mean, I don't know if you can make the argument that with that osmotic flow and creating more or a greater tension, because if you ever get a pump, like you said, and then you try to pull the muscle, it feels like there's a lot of tension going on.
Yep.
I don't think that creates greater single fiber force. I think it creates more internal tension in the muscle, but I don't know if that creates like greater single muscle fiber?
No, it can. So osmotic fluid shift can increase single fiber force. This has actually been known for quite a long time, particularly in the 1970s. There were quite a few papers on it. And this is possibly one of the benefits of warm-up, of course, for speed and power. Because remember, water is a polar molecule, which means it has obviously oxygen, which is negatively charged, and two hydrogens, which are positively charged, which means one end of a water molecule is more positive and one end of a molecule, because oxygen will be here, is more negative. And that affects how myosin and actin bind, because remember, they are charged proteins. And I think I said earlier in the podcast that having an increase in intracellular water tends to reduce the likelihood that myosin will detach. So it tends to hold or bind myosin for slightly longer, increasing fiber force. It doesn't seem to increase fiber velocity. I think there was a really nice paper published in 2015, and I've forgotten the first author, could have been Sato. But because it increases force, if you look pretty much along the whole force velocity spectrum, you'll see an increase because the force component is increased. So it looks like osmotic fluid shifts improve both peak force and also what you might call, or a lot of people like to call, power. That is the ability to develop force at higher and higher velocities. How it affects eccentric is a bit more complicated. Obviously, eccentric, you're trying to stretch the muscle, which means theoretically you need the cross-section to be reduced in magnitude, and water will resist that. So it could be that as we're fatiguing in a stretch, shorten cycle type activity, that flow of water is actually helping to minimize the force loss. Because as we get an active force loss, we're also getting an extra benefit from not only water helping at the actin-myosin cross-bridge, although remember, in eccentrics, the cross-bridge may not be the primary reason we're so strong, and I'm unaware of the effect of water at the titin level. I just don't know it. I don't know if it's been looked at. But the whole muscle still would have to stretch, and that means every fiber has to stretch, and that means that if you've got more osmotic fluid pressure minimizing compression, it also means you can't stretch it. So you need a higher force to stretch it, and this would partially overcome the loss of force with fatigue. By the way, again, just a hypothetical, you might have heard that sodium bicarb, helps to minimize fatigue in particularly repeated sprint stuff. And in swimming and rowing and cycling, we see quite good effects of it. But in things like repeated sprint running, we don't. And it could be because the sodium bicarb is in some ways a buffer for the hydrogen ions. It might be affecting the osmotic fluid shift, but it also might be that in running, our ability to bounce off the ground is actually improved a little bit with all the fluid flow into the muscle. So there's simply less opportunity for the bicarb to be effective, because if we can, as long as we can still bounce, we can still run pretty fast. Yeah, even if the actual muscle work in the hip flexors and extensors declines a little bit, we just bounce a bit more, and that might be effective. So it might be the reason why sodium bicarb is a little bit less effective is because the water mass actually helps us in stretch shorten cycle activities more than in what you might call more concentric dominated activities.
And I think it's nice to see how everything you spoke about in the beginning kind of helps explain some of the things that we're talking about now. Like it all kind of ties in together a little bit. And that's why it's important to have a strong understanding of basics, because you can begin to apply it. Now, this leads to the final reason what people think that eccentrics, or the growth that comes from eccentrics, or regardless of muscle damage, because of, I know there's some contention whether mechanical disruption occurs during or immediately after eccentrics. From what I spoke with, like people who look into this, like Dr. Tabuchi and Kano in Japan, they think that there is no mechanical injury, that damage is a pure biochemical process, because we see damage occur hours later, and there's no membrane disruption, even though it might feel like membrane disruption and sarcomerogenesis disruption and micro tears, whatever that means, because that's kind of thrown around. So despite that, it's just pure biochemical because of those stretch activated channels opening, and then we begin to see the disruptions occur later on. I mean, that's from what I'm familiar with. But like you said, you have the repeated bout effect, and those sacs can get tighter in a way, and along with other mechanisms like you mentioned, and I think you have a good article about this too for people to check out. I could link that below. But people think that the main benefit from eccentrics is the addition of adding sarcomeres in series. And that is why we see an increase in fiber cross-sectional area, because there's this paper from Hornberger suggesting that longitudinal growth can impact muscle fiber thickness, at least mid-belly thickness. But the thing is, you just came out with a paper kind of going over the data showing that eccentrics is not convincing that they add sarcomeres in series. And if they do, it's likely an insignificant amount. And so I can't put my head around the idea that if we add such insignificant amount of serial sarcomere numbers, that can lead to that increase in CSA that we see from eccentrics. That's how I think of it. I don't know if that's wrong.
Okay, let's try and unpack this a little bit, and you can just keep asking me questions if I miss a few things. First of all, I just want to go back to the muscle damage. I mean, I agree with those researchers that it's largely biochemical. At least based on the current evidence, I would argue that that's the best model we have. I would argue that it is always possible for that disassembling of the sarcomere that's triggered to occur even during the contractions themselves.
Just a little bit, right?
Yeah, but that it just takes a long time, several hours for it to really peak. And of course, somewhere along the line, we're also losing calcium release. So that triad junction that has to take down the T tubule, has to take the action potential and has to turn it into another calcium signal that releases the calcium. That seems to be strongly affected somehow by mechanical stress or reactive oxygen species, or something is affecting that. And so you're losing calcium release. So that's why you often hear of low frequency fatigue or something like this, which means that we're losing the ability to release calcium. So they seem to be the primary factors. And then over the next few hours or day or two, it really ramps up and we're disassembling the sarcomere and then we're rebuilding it up. And it's not a destruction of the sarcomeres. It's not a destruction of the fibers. It's not micro tears. Having said that, just to remind your listeners that if you can see it in humans, but you definitely see it in all the animal models, you use electrical stimulation. Electrical stimulation itself can directly damage the fibers. If we use electrical stimulation in humans or in animals, you actually can get proper damage of the fibers to the point where the fiber undergoes necrosis. Luckily, the membrane of the fiber remains somewhat intact, and then we can start donating stem cells and building new myofibrils, and we can rebuild that fiber. But that is very different to human voluntary muscle contractions. In voluntary contractions, even under the most extreme cases of running a marathon or doing 300 maximal voluntary contractions, maybe fewer than 1% of all your fibers will undergo that necrosis. And in the gym, when you get sore, it's probably 0. So yes, it's mostly biochemical. I think we know that under voluntary stimulated conditions, it's only in NMES type stuff. And nowadays that's known better. You use the NMES in animal models to actually study muscle injury, which is very different from just DOMs. Okay. But let's get to the eccentric stuff, because that's really interesting. So I said a little bit earlier. So first of all, it does look like maybe with aging, we can lose sarcomeres in series, whether that's the deconditioning and detraining that then causes it, or if there's something about the aging process that causes it, or whether it's both together. You know, if you detrain as a young kid, it's no problem. But if you detrain as an older person, you don't move your muscle through a large enough range of motion, it starts to lose some sarcomeres. And then that causes more problems because now you can't move through a range of motion, so you don't, and it exacerbates it. With certain diseases, cerebral palsy, spinal cord injury, people who have a lot of spasticity, that turns into contracture. We mentioned Rick Lieber before. One of the better, frameworks or models of how we think contracture works, which is different from spasticity, which is like a reflexive, when you stretch the muscle or you get some sort of stimulus, it goes into spasm because of that. Contracture is just an ongoing problem. And that's both at the extracellular matrix level. There's a whole bunch of stuff going on at the extracellular matrix. And also at the fiber level, maybe there's some loss of sarcomeres because you've got a chronically shortened muscle under spasticity with lots of calcium. but also that means that when the muscle's at normal length, the sarcomeres are a lot now longer than they should be, and that increases the passive stiffness. So, you know, I'm trying to give you an example of some conditions or populations under which we might want to not just change the extracellular matrix, but also add sarcomeres in series to improve muscle function. As far as adding sarcomeres in series to prevent muscle damage like DOMS, I don't think that's the case at all, because that's not why they're getting damaged in the first place. And I think there was a really nice paper from the Canadian group.
Howard.
Yeah, I think Avery Hinks might have been the lead author. Yeah, so Jeff Powers' lab, showing no effect of sarcomere addition on, you know, DOMS or whatever. And that makes heaps of sense to me, that you're not trying to do that. Same with muscle injury. Again, we said, oh, you know, you strain a muscle, therefore if you add sarcomeres in series and each one doesn't have to stretch as far, the muscle should be safer. According to all the evidence I've seen and experts in Denmark and Sweden who do the research properly, most muscle injuries are at a connective tissue level. Of course, you'll have heard it, you know, on the tendon and on the aponeurosis, but even a mid-belly injury appears to be occurring at the fascicle level, at that perimysium, or even if fibers are damaged, it's the extracellular matrix that seems to be letting go. And, you know, as one expert said to me, Peter Magnuson, well, Tony, if it was an actual muscle injury, it would recover within days. And the fact that it takes weeks to recover from the injury reminds us that it's actually extracellular matrix, which takes a lot longer to recover and can, of course, get scar tissue in it. So just adding sarcomeres there is probably not what you're trying to do to minimize injury risk. It's way more complicated than that. So for the average person, we probably don't care about adding sarcomeres in series. I mean, I guess theoretically, if you have a pennate muscle and you add sarcomeres, your muscles look bigger. So maybe if you're a bodybuilder, you would. If you're a sumo wrestler or a weightlifter and you're moving through large range of motion, for example, at the knee, because you go all the way down to the ground and then all the way up under high force, you probably want a few more sarcomeres in series to broaden out your force length relationship, because you've got to work through such a large range of motion. So I guess, yeah, there are times we want more sarcomeres in series. And so if that was your goal, what would you do to get it? Well, over 150 years of research, it really does point to the fact that if you have a muscle force, whether it's passive or active, that is sufficiently there at long lengths, you will add some sarcomeres in series. And this seems to be a trigger during muscle growth as we grow from kids to adults. It appears to be the case if you use limb distension surgeries, where you deliberately break the bone and pull it out. The muscle has to grow longer very quickly, and that seems to happen through the addition of sarcomeres in series. Just to remind you that if you add sarcomeres in parallel in a pennate muscle, you also get a longer muscle. And in some muscles, growth with aging, of course, as we go from a kid to an adult, also partly occurs through what we might call traditional hypertrophy. And people say, oh, that expands the aponeurosis. Well, of course it does, because you have to stretch the aponeurosis. But typically, adding sarcomeres in series is the way we think we majoritively get muscles longer. And it makes sense, therefore, that if a muscle has to either work through a large range of motion or at some long length, we would add sarcomeres in series. Now, in the animal world, we know, for example, that if you had two monkeys that live in the same environment, that have the same physical activity habits, have roughly the same diets and everything else, but one of them tends to eat bark with a wide gape at the jaw, so they're just doing a small amount of their time, but producing force at a wide gape. If you just look at those jaw muscles, even though everything else in their environment is the same, the one that uses the wide gape adds sarcomeres in series and has longer fibers. If you look at animals, again, in the jaw muscles, and try and understand at what length do we have an optimum overlap of our sarcomeres? In other words, we think we're adding sarcomeres to optimize force at a certain length. What length does that occur at? Well, it seems to occur at the point at which the maximum bite force occurs, which we very rarely do, because most of the day we've got our mouth closed, or the animal has its mouth closed. Sometimes it yawns to a really wide gape, and sometimes it chews here. But if it has to chew sometimes at a high force here, it will adapt to that relatively rare instance where it needs a long length at high force, and it adapts to that. So all across both growth and development and looking across species in the wild, it really looks like the length of the muscle, or maybe the excursion range of the muscle, is the primary factor influencing sarcomere number. Of course, your listeners will maybe know that there was some studies done by Dave Morgan's group in Melbourne, one published in 1994 by Lynn and Morgan, another one repeated actually in 1998. And they ran rats uphill and downhill. And the idea was, well, muscles got sore in the rat when it ran downhill. And we think that must only happen with eccentric contractions. So we think that running downhill is eccentric and running uphill is concentric. So it's a wonderful model to look at the effect of eccentric training. And they thought it makes sense, again, that if you add sarcomeres in series, you might not get as much DOMS and you may not get as much muscle injury. I'm not sure that that's right. But even if you believe that, you say, well, maybe repeated eccentric actions could add sarcomeres in series. It makes sense because in the 1970s and 1980s, people had lengthened muscles and immobilized them at long length. And they added sarcomeres. So they thought, oh, maybe there's something about this stretch stimulus that's important. So if we do active stretch, we should get a really nice response. And in the vastus intermedius muscle, very important, by the way, that's not just a throwaway line to sound cool. The vastus intermedius muscle of the downhill rat increased sarcomere number. And the vastus intermedius of the uphill rats reduced sarcomere relative to a control group that was caged and didn't do anything. That was not only shown in 1994 and 1998, but was repeated in the 2000s by Tim Butterfield working in Walter Herzog's lab, who also did uphill downhill running, also studied VI, the vastus intermedius, and found the same thing. Repeatable finding 3 times, 2 different labs, love it. But in the Tim Butterfield lab, they said, well, in the Walter Herzog lab, they said, well, but are these muscles actually eccentric and concentric? So they put little crystals, sonomicrometry crystals in the muscle, and they put ultrasound over it, and they can see what the fibers are doing. And you put a little electrode in for EMG and say, well, when the muscle is active, what's the fiber actually doing? Now, you can't study the vastus intermedius because, like in humans, it's deep. They could study the vastus lateralis, though. And in the vastus lateralis, if you look at their data, look, I think on average, they probably were eccentric in the downhill group, and it was probably mostly concentric in the uphill group. What I will say, and you notice it if you go and look at their graphs, is that the EMG was active generally at the short muscle length. Regardless of whether it was eccentric or concentric, it seemed to work quite short muscle length. And in their paper, what you'll see is that the vastus intermedius does what you would expect it to do, but the vastus lateralis does not. It lost sarcomeres in both conditions. Now, it is true that in that one paper, they nicely show one outlier. And so the downhill group did not reach statistical significance. This is a problem in science. It was clearly not different to the uphill group. And by average, it lost a lot of sarcomeres. But that one outlier meant that it wasn't statistically different. So if you want to be, if you want to read it, you'd say in VI, yep, added sarcomeres in series downhill and lost them uphill. In the VL, they lost them downhill, but no change in the downhill. Sorry, lost them in the uphill. No change in the downhill. But I would argue that in the downhill, they lost them. And that was really interesting. Partly because if it really was eccentric and their sonomicrometry suggested it was, why did it lose sarcomeres except for one rat? But second of all, I noticed that according to their data, it seems like the muscle works at a short length. And since the VL works at a short length, it made sense that both of them lost sarcomeres if muscle length is the key. Now, we have no idea in these studies what the VI is doing. The VI changed the way you expect if eccentric was an important stimulus, but we don't actually know it was eccentric. We have no idea. Go on to another way of doing this. You could actually do electrical stimulation and actually stretch the muscle. Okay, it's not a voluntary contraction, but it is definitely eccentric. There is no doubt about what's going on. So what happens if you do this? Well, if you do this, you can find increases, decreases, or no change in sarcomere number. So that's right. You can literally find decreases in serial sarcomere number in eccentric studies using NMES. In fact, in the same muscle, you can find increases and decreases in different regions of the same muscle, even though the whole muscle did an eccentric contraction. The best explanation, according to Walter Herzog's extra studies on this, was that there was something about the strain magnitude, that if the fibers had to stretch a lot in the eccentric, they added sarcomeres, but if they didn't, they could lose it. And again, this suggests that it's something to do with the strain, or the muscle length is more important than the contraction mode, that it's not just that it was eccentric, it's that it went a long way or went to a long length. So the question then becomes, well, is eccentric actually the key stimulus then, if you can literally lose sarcomeres doing eccentric training? Well, another way to look at it is, what percentage of sarcomeres do you gain? Let's say we do gain sarcomeres. You know what? I'm unaware of an eccentric study where we know that it was an eccentric contraction. So the VL of downhill rats, or any of these NMES, these electrical stimulation studies, where we know it was eccentric, I think the biggest I've seen is maybe 5 or 6% change in sarcomere number. If you look in downhill rat studies where it doesn't matter which muscle they look at, you have no idea if it was eccentric or concentric, you just assume it might have been eccentric because it ran downhill, the biggest I think I've seen is about 9%. Either way, if you take all these studies, you get about a 4% overall increase in sarcomere number across all the studies at which it's claimed that it was eccentric, right? That even if we're not really sure, we think the model was eccentric, right? 4%. If, however, you do if you do immobilization at long length, you can get 15% or 20% change. In one study that did what they called moderate length isometric, they got about 20% increase in sarcomere number. And at long length, again, isometric, 32% increase in sarcomere number. So sitting the muscle at a long length passively or activating it actively at long length is giving you what, between 15 and 30-something% increase in sarcomere number. Whereas even if we believe that a lot of these studies actually had eccentric action in the muscle, and we don't because they're calf muscles in rats running, where they're probably shortening actually, we get an average of about 4%. So this suggests that certainly eccentric exercise in and of itself is not as big of a factor as activating at long muscle lengths or resting them at long muscle lengths. And I think I would argue, based on the evidence, that if the eccentric studies are actually adding sarcomeres, it's probably not the eccentric mode itself that's doing it. It's that eccentric training is a nice way of adding a nice big muscle force and then getting your muscle out to a long length. So then, to me, really it came down to, is it the length of the muscle, or is it something about the strain, the actual length change? And by the way, strain can be positive strain, so shortening. So if you shorten or lengthen the muscle through a large range of motion, if it has to work over a large range of motion, is that what stimulates the sarcomere number? And while it probably can, we can't discount that, it looks like it's the maximum length itself. And that makes heaps of sense, because if you hold it at long length immobilized, it adds lots of sarcomeres, even though there's no strain. And if you do isometric training where there's no strain, well, if anything, the muscle shortens a little bit, right? Because you've got a series elastic element, so the muscle might shorten a fraction, but it's really producing force at long length. You get a really big sarcomere number. So it looks like it's the ability for the muscle to actually get to its longest length at which it either sits for a very long time or has to be active that sets the number of sarcomeres. And maybe under some conditions we can kind of get that with eccentrics, but even if we do, it doesn't seem to be anywhere near as effective as just getting it to a damn long length and activating it, or even keeping it there for a few days. So I would argue that based on the current animal evidence, eccentric training is not a primary stimulus for adding sarcomeres in series, and may in itself not be a stimulus at all. It just might be a reasonable way of stretching a muscle out to a long length while it's got a high force.
This leads to people actually saying that there are some muscles that can't experience sarcomeres in series. because they don't reach deep down to the descending limb. So for example, the quads, when you do eccentric training with the quads, you statically stretch them. They can experience serial sarcomere number, but for a muscle like the biceps, where they operate on like the early plateau and ascending limb, their sarcomeres don't reach very far down the descending limb. So there's not enough passive tension to stimulate this serial sarcomere number.
Well, I'm not sure that it's when we say, yeah, I have to talk about this with my PhD students too. When you say passive tension, I think that means the tension in the muscle when it's relaxed. And I don't know that that's the primary signaler, but maybe what you mean is that it could be that the signal is coming from what we might call or what we used to call a passive element like titin. It could be that one of the regions in titin, and certainly a hypothesis we think might be reasonable, is the signaler for this thing. But remember that titin is also an active force producer, because the binding of titin, well, during muscle contraction, parts of titin also coil and uncoil, and they can develop force when they do. So actually titin is an active force producer. It's just tiny for that little bit that coils up. And second of all, because it can stiffen itself and because it can bind to titin, when it's in the active muscle state, we might need to be really clear on what we mean by passive here, because it's working during active muscle contraction, and calcium is literally activating the titin to change its properties. So I don't like the term the passive stretch that's causing the signal, because it seems confusing to me, and I hate confusing language. I want to be really clear here. So I guess what is feasible is that actually, you know what, I'm going to ask you, now that I've done that, can you rephrase your question so that I can get my answer really straight without going through a figure of 8 here? Can you rephrase your question?
So in a muscle like the biceps, people
perfect
that are fusiform, so they have long fascicles, or that run almost the entire length, most of them do, I think, of the muscle. There are claims saying that in order for a muscle to experience sarcomeres in series, there has to be a sufficient threshold of passive tension. And they use the term passive tension. And they go, well, the biceps, they operate on the ascending limb, which means that they don't reach deep into the descending limb to therefore experience sufficient passive tension to then experience the sarcomerogenesis. But a muscle like the quads, they can stretch very far into the descending limb and therefore reach that passive tension threshold to stimulate sarcomerogenesis.
So first of all, maybe the reason why people still talk about passive tension is because immobilization at a long length is such a good stimulus for sarcomere addition, based on the animal data at least, that, you know, the idea that you only actually need a passive stimulus. And so it makes sense that whatever is triggering it can be activated passively, and therefore it's a passive stimulus. Okay, so let's just clarify that. But also let's clarify that it appears, based on the evidence that we've reviewed so far, that if you activate the muscle at a longer length, you get a much greater adaptation, and it also looks like a much faster adaptation. And that even if you immobilize at a short length and only do a small amount of active contraction at a long length, you either don't get any loss of sarcomeres anymore, or you even lengthen it. So based on our current understanding, length is the primary determinant, but force seems to be an amplifier or a multiplier. So it's not just that the passive force causes it, because when we activate the muscle and we have active tension, we seem to get a much bigger response, more sarcomeres in series and faster. So I'll just clarify that, right? But then when we come back to muscles in vivo, first of all, let's say we don't know, because we've never measured it and never done it accurately. So everything here is speculation, and that's all we can do. My question is this. If we have to go to a long length to get additional sarcomeres in series, do we mean long length relative to the current force length relation of the muscle? Or do we just mean that we put the muscle at a length that is unusual and rarely seen by the muscle. Now, according to sort of in vivo type animal studies in the few muscles that have ever been studied, and a reminder for your readers who might know Vince Caiozzo's work, and he published a paper in 2000 that had this nice model that seemed to fit the data, that once you go past a sarcomere length of about 2.7 microns, you know that the sarcomere is now long enough that it starts to add sarcomeres in series. And that would simply suggest that if you're working somewhere reasonably down the descending limb, that's the primary trigger. And maybe if you activate the muscle there, you get calcium, you get more molecular signaling, and maybe that's the amplifier. Having said that, isn't it interesting that there are muscles that, at least under maximal conditions, are always working on the ascending limb? I mean, didn't we just say that, I mean, if you're on the descending limb all the time, you should add sarcomeres, and if you're on the ascending limb, therefore, you should lose sarcomeres. If the muscle works at short length, it should lose it. Just like in the rats that have run downhill, but I said the sonomicrometry looked like it was working at a short length, and they actually lost sarcomeres. Uphill running in rats lost sarcomeres. Now, don't get me wrong, when you do all the uphill stuff, you don't find statistical significance in a meta-analysis. But a lot of people have the theory that if you're working at really short muscle lengths, you should lose sarcomeres in series. So if that's the case, and our calf muscles are always working on the ascending limb, why haven't they lost sarcomeres so that they can work at optimum? So I don't know that it's as simple as just working on an ascending versus a descending limb. Of course, there is a possible explanation, and again, it comes down to us understanding that you have a series elastic element, that the higher the force, the shorter the muscle. So when we do a maximal contraction and measure the force length curve, the calf muscles, for example, look like they're really on the ascending limb. And only when you go right into dorsiflexion can you stretch them far enough to be at the plateau or maybe just onto the descending limb. But of course, when we're walking, we're nowhere near maximal activation, which means the Achilles tendon is a lot shorter, which means the muscle is a lot longer. So it's very possible that we are actually working really short during walking and running. None of this makes sense. I mean, why aren't we losing sarcomeres? So I don't know that it's just the sarcomere length itself relative to its optimum length that is the primary trigger. What if it's far more complicated? What if your extracellular matrix is adapting to the length at which it normally works? And then if all of a sudden the muscle has to work at a longer length, extracellular matrix is somehow signaling to the genome within the muscle fiber, hey, I'm always on stretch here. I'm going to need to reorganize my ECM, and I'm going to have to add some sarcomeres in series because remember, I've got desmins and integrins that are communicating with me. And if you're always at this long length, I'm always got this bloody weird sort of signal coming through. If you could just add a few sarcomeres in series, so I've got these, the Z bands are closer together, and therefore I've got more normal signaling coming through from the Z band associated proteins, everything would be nicer for me. Thank you very much. And so it could be that we adapt relative to the length at which the muscle commonly operates, and that some muscles through genetics or something are always built to be on the ascending or descending limb in normal activity, and that if you then try and change that length, it will adapt to go back to working on its ascending or its descending limb. And to be honest, I don't know the answer to this, but I definitely have the question, is it relative to the force length relationship, or is it relative to the lengths at which you see in daily life? And remember, in the quads, we walk, we run, we walk up and down stairs. The majority of humans are not flexing their knee past about 40 degrees of flexion. So if you all of a sudden do knee extensions and squats even to 90 degrees, that's longer than it normally would be. Yes, it's also just onto the descending limb for the quads, but it's also just long relative to what it's used to. And same with the biceps. I mean, yeah, you say the biceps might work, but we're always holding stuff with our elbows extended, and we're always picking stuff up from long length towards short length. So we're very often working our biceps at a long length in daily life. So regardless of whether it's on its ascending or descending, wherever it's set right now, we're not really able to work it at an even longer length unless on one of the heads, you extend at the elbow and at the shoulder and start doing it. So maybe this is why muscles do and don't adapt. It's because it's relative to daily life. And I think this is one of the questions that we need to start looking at in the future is if we have an aging population or a clinical population in which we really do believe that adding sarcomeres in series will be useful, in addition to neurologic benefits, extracellular matrix adaptations, and everything else that's also going to happen that is probably also really important. If we think sarcomerogenesis is key, what is the signal? And I would argue it's something about length, not strain so much, and not the contraction mode so much or at all. And it may have something to do with force. So actively contracting the muscle at long length might be more important than short length. But what the definition of long length is, I don't know. Does it just mean anywhere on the descending limb, or does it simply mean longer than it would normally be used in that person's current daily life? Does that make sense?
Yes. And I think that helps people give something to think about rather than a direct answer. And that leads to the final point that we will get to today. When you're thinking about the bicep, about training it behind, there's a lot of data when it first started that training muscles at longer lengths led to greater hypertrophy. But now we see with muscles like the biceps, they don't really seem to benefit longer from they don't seem to benefit more from longer lengths. And for example, Dr. Jared McMahon, he says, well, you can't really stretch the biceps with a shoulder extension position as that's mostly tendon. And he told me he measured that in vivo.
Okay, cool.
So he thinks it's something else. He thinks that when he first started, he goes, well, maybe it has something to do with a little bit of passive tension, not too much, because too much passive tension could offset the active tension. And he believes that active tension is more important than passive tension, but he thinks a combination of both is nice. And then something to do with internal, external moment arms as well, and training a muscle at its optimal length for greater force production. And so others argue that it's mainly length, and we see increases in cross-sectional area or increases in strength from passive tension. And some might say, well, that's increases in sarcomeres in parallel because sarcomeres in parallel increase force production. But then there is that something to think about. It's like, well, if you add sarcomeres in series, don't you also clip costomeres to these new sarcomeres, and can't that increase that lateral force transmission into greater force production?
Well, I don't know that just adding some sarcomeres and adding more crostomeres will necessarily increase lateral force transmission, because you're trying to transmit the force that comes somewhere near the costomeres, which means within the adjacent sarcomeres. So if you've got more sarcomeres, you'll need more costomeres. But if you add some more sarcomeres, I'm not sure that that's the case. So first of all, we need to make sure we differentiate between sarcomerogenesis, so the lengthening of the fiber, and just gross muscle hypertrophy. That is, maybe we'll call it radial hypertrophy, as seen in a muscle biopsy sample. By the way, just to be clear, eccentric training does increase radial hypertrophy, because we can see in muscle biopsy samples of at least 4 studies that I know of quite significant radial hypertrophy. Now, if that we think is caused by an increase in the number of myofibrils that are donated into the cell, right? That could be slightly to do with an increase in the size of the myofibrils, but mostly just an increase in the number of myofibrils. It is possible, and it's been known for a long time, and of course you brought it up before, I think Troy Hornberger, that if you have myofibrils that aren't spanning the entire length of the fiber, that lengthening them out can increase the size of a fiber. And that's true. Depends where you measure it, of course. Because I would have assumed, to the best of my knowledge, what we think is happening is that the myofibrils don't always run all the way to the end of the fiber, because fibers taper. Now, when we take a muscle biopsy, say in vastus lateralis, we take it right in the middle of the muscle belly and about 2 centimeters deep. And if you're looking at your fascicles like this, what we think we're getting is somewhere right in the middle of the fascicles, and assuming if those fascicles, because if we were really superficial in the muscle, what you'd actually be getting is the end of a fascicle. But because we're deep in the muscle, we seem to be about halfway. We're getting in the middle of a fascicle. And assuming even if the fibers within the fascicle don't run the whole way, we think the fibers are pretty much in their central bit, which means if you then look inside the fibers, we'd be assuming that the myofibrils are also fine there because it's at the end that they might not be reaching. So while you could get gross muscle hypertrophy through a slight elongation of those myofibrils, which then increases the width of the fiber at its tapered ends, I'm not sure that that explains much. It might be a little bit because you could have some myofibrils that run here and then they get a bit longer, right? But if you take a biopsy here, I would have thought the lengthening of the myofibril will have a very limited effect on the radial hypertrophy seen in a muscle biopsy that's taken in the middle of the muscle belly. Does that make sense? Notice how perfect I'm trying to be here. And so when we then see the increase in radial hypertrophy in studies on eccentric training, I would argue that that's pretty good evidence that we're majoritively seeing either an expansion of the myofibrils or an increase in the number of myofibrils within the fiber. Some of it could be sarcoplasmic or fluid, right? Now, the second thing is whether an increase in fiber length could contribute to muscle hypertrophy. Well, it could, because in a pennate muscle, if you increase the fiber length, so now not just talking about the myofibrils and radial hypertrophy, we're talking about whole fiber and therefore whole fascicle lengthening. Absolutely it can. Just from a geometric perspective, if it goes longer, you'd expect a bigger muscle, right? Of course, that doesn't account for the fact that fibers often curve a little bit, so it might not be as much as you expect. You also got to argue, though, that if the fibers actually got much longer, then the whole muscle would get longer. Where does your tendon go? So if all of these increases in fascicle length we see are true, we should expect really big shifts in force-length relationships. By the way, we don't see that. Massive changes in velocity capacity, which we tend not to see. And we should see that the tendons get really, really slack at their ends, which we don't see. So what we see as fascicle lengthening on resting ultrasounds might be a problem with how we're measuring it, or it might just be that how the muscle sits. And then once it's, by the way, when we then measure it during active muscle contraction, we often don't see the fascicle lengthening that we see at resting muscle. So that hints that maybe it's just the fibers or the fascicles resting at long length. Either way, if you could add sarcomeres in series, you could get some hypertrophy. So it could be that in conditions, however, where we're pretty sure we've lost sarcomeres, aging maybe, forms of disability, spasticity, contracture, maybe if we could add sarcomeres in series, this would then contribute to hypertrophy. Yeah, really important. The final question, though, is if, sure, the current stimulus says that muscle length matters, although in humans who are fully active, we're probably moving through such ranges of motion and we're not really going to lengthen fibers anyway, even if we worked at long muscle lengths. But if you could then, stretch a muscle out to a really long length and train at the long length, should we get more hypertrophy, regardless of whether that's because the fibers got longer or because they got radial hypertrophy? Because I'm going to argue that we're probably not making these fibers much longer through adding sarcomeres, I would say that what you're really getting in hypertrophy of a muscle is radial hypertrophy. And that not only increases the size of the fibers, which directly impacts hypertrophy, but adding diameter means that the next fiber also gets pushed away. Yeah. And as it gets pushed away, pennation angle rises. And if you have the same fascicle length, then an increase in pennation angle increases the size of your muscle. And Per Ogle showed that really nicely, I think, in a 2001 paper where he took the muscle biopsies just with traditional heavyweight training and showed that both the increase in the diameter of the fibers and the resulting increase in pennation sort of work together to account for the gross muscle hypertrophy. So now the final question in your statement then comes down to, can training at long muscle length increase radial hypertrophy of a fiber? Is it possible that there's a better molecular signal for hypertrophy? And the answer is yes, it is very, very possible. And this might be why we get more hypertrophy at long muscle lengths in some muscle groups that you nicely point out, because people like me, we study the quads, and it seems very, very clear in the quads that If we work at a 90-degree knee angle, 100-degree knee angle, we get nice hypertrophy. If you work at 30-degree knee angle, you pretty much don't see any hypertrophy. So it seems to be really clear for some muscles. But as you pointed out, in a lot of the upper limb muscles, we don't see that. And I think I saw another study at the European College of Sports Sciences, the ECSS conference recently, even in the plantar flexors, that muscle length had no effect, that it didn't matter if you trained at long or short muscle length, you got the same overall hypertrophy. I think they used MRI. It was a pretty good study if I remember it, because I thought I'd put it in my mental memory bank for you. It looks like in some muscles, this is not the case. And it could be that by long length, we mean on the descending limb, which might stretch the fiber enough to let in more calcium through the stretch activated channels to get a better signaling response to the genome. Or that the long length alters the properties of titin, alters the mechanotransduction, and that might be somehow causing a stimulus. That's very possible. Or it could just be that if you work the muscle at a longer than normal length, you get it. I don't know which one it would be. But if your muscle is always working through those long lengths, and let's say it's the stretch activated channel hypothesis you're going with, well, if you're always working through large ranges of motion, maybe those sacs aren't releasing more calcium into the muscle fiber, into the cell. Or maybe because you're always working through long length, titin is no longer uniquely sensitive to it. So it doesn't matter if you do training at long length, you're getting normal hypertrophy at long and short lengths because it's equally sensitive. So this is where I don't know. I don't actually know truly the effect of muscle length on hypertrophy, except to say that in some muscles, in people who are previously untrained, it looks like muscle length does matter. And then in other muscles, it doesn't seem to matter. And I don't know if it's the ascending, descending limb thing. I don't know if it's the shorter or longer than normal use thing, or whether it's some genetic aspect that we're unaware of. For example, in muscles that do a lot of isometric work, like in the upper body where you're holding stuff, or in the plantar flexors, they're not amenable, whereas in work-producing muscles like the quads, they are. And I, to be honest, I don't know. What I would caution, because I do know that a lot of people say muscle length matters, and to be fair, because I often deal in the lower limb, I find myself saying it myself, and I need to watch what I say. Whilst it is true that in some muscles, under some conditions, muscle length seems to be critical, it definitely is not the case in all muscles, and we don't know exactly why, and I don't know even which muscles, because we need a lot more repeated studies to make sure that it's a repeatable finding for these muscles. Reason why this is important, take the hip thrust. People think the hip thrust is awesome, but of course has high activation, big osmotic fluid shift because it's metabolically tiresome, but it's a very short muscle length. So if muscle length matters for the glute, hip thrust shouldn't work, right? So we really do need to look at some of these things and find out the answers. And I'm afraid that's going to be one of these, we need more research to truly tell. What are your thoughts now?
I mean, I always just stuck by the idea that some muscles may benefit more than others, as you stated. And I think it gets, like you said, it gets a little complex, because with the glutes, or with the quads, I mean, when you go to like anything past 90 degrees, it doesn't seem to be that beneficial. So it's maybe that you don't have to go to such a long length. With the biceps, I don't know if compare the bottom of flexion to the top, if that makes a difference. With the glutes, maybe it could be more edema, but you would think more edema occurs with longer lengths because of damage. And so that extra hypertrophy could just be edema. But people think that if a muscle benefits at long length, it's because it has a greater moment arm. And because it has a greater internal moment arm, the brain is going to recruit that muscle preferentially and then suggest, hey, that's going to be the prime mover or whatever. And that muscle is going to get the most activation or be preferentially recruited. And they think that like the brain recruits muscles based on their internal leverage. So the glutes have better internal leverage in hip extension. So they think that's why the glutes still grow pretty well in the hip thrust, because of their internal leverage. So the brain preferentially grows the glutes.
Yeah, I'm not convinced of that. I mean, I have to go right back into the data on our understanding of activation. First of all, we really need to be mindful of EMG, because remember, EMG is awful to try and understand how muscles are activated. Even if you have a comparison, you say, is the muscle more active in A versus B? We're leaving the EMG electrode on the skin. It's the same person doing the same thing. We've just changed the moment arm, or we've changed the hip angle or something. Look, EMG was much greater here than here. It must have been more active. And that may not be the case, right? Because the muscle is moving under the electrodes. There's more compression of the adipose tissue. There can be a change in the amount of activation that's different along the length of the muscle. In other words, underneath versus away from the electrodes. And even the fact that if the motor unit firing changes, the shape of the wave or the action potentials change. So when they get all the way through all the filtering through the tissues and get to the EMG, and they all get added up because that's all they do, and they add up, and then they also the positives and the negatives cancel out. The way the action potential shapes change affect the way they add and subtract at the electrode, and that can completely change the EMG. Of course, just recently, you'll have probably seen some studies where people have used the OpenSim modeling, which again has its issues around trying to understand what the actual muscle forces are. That's not perfect either. But what it is showing is that there's a mismatch between how the EMG is changing and how we estimate the muscle force itself is changing, suggesting that the EMG might be leading us wrong. Now, who knows which one is right and wrong, to be honest, but the fact that they're giving us completely different results is another reason to just wait. But also, remember, we've sort of talked a lot in the last fair while in this podcast about the fact that there are probably multiple mechanisms that either are required for hypertrophy, or at least they're affecting the level of hypertrophy. They are permissive, rather than necessary. And it could be that there's something to do with muscle length. It could be something to do with activation. There's good evidence that we activate regions of muscles whose fibers happen to be at the optimum length during a contraction. And it's got nothing to do with the overall moment arm, because even within a muscle, different regions are differentially active. People have often shown, for example, during hip flexion, that the more proximal part of rectus femoris is active, but during the extension, the more distal part is active. Now, if it was just moment arm, the whole muscle should change up or down, not one region versus another region. So I'm not confident that it's just to do with a moment arm. It is true that it makes sense that your brain is able over time to learn how to activate the muscles in a way that gives the best likelihood that a movement will be performed. So if you're practicing the squat lift over time, it makes sense that it will reduce activity of some muscles and improve the activity of other muscles to have the best outcome under those conditions. And it makes sense that if you're lifting a very, very heavy load slowly, that it might learn that some muscles have a bigger physiological cross-section, has certain architectures that are more amenable, that its force transmission within the synergistic group is more optimum, and that its moment arm is a bit bigger, and therefore it activates them more. But remember, you've got multiple joint rotations trying to get a vertical movement of a bar. So if you say, oh, I'm going to use glute more, and then glute changes the force vector and you lose balance, you're in trouble. So even with that, you can't just say, oh, the moment arm is better, I'll activate it more, because it'll actually throw you off. It gets so complicated that I'm just not confident we can say that we activate based on the muscle architecture or its internal moment arm. I think what we've got to do is find a way that the muscle is working really bloody hard for a reasonable amount of work. So it's got to do some metabolic work. It needs some time under tension. And then if something like the muscle length or the contraction mode matters, that will be the 1%ers rather than the key strategy. And this might be why we benefit more from doing lots of different exercises, because our body simply has to optimize each exercise. And of course, that means different muscles are going to work differentially hard as far as force and work are concerned. And so if we do multiple exercises, we end up getting them all somehow. And I don't think we're at the point now where we know enough We almost need multiple muscle biopsies across the body to actually look at the signaling response. One day, what we might have is imaging that allows us to estimate the signaling response rather than just activity or temperature or metabolism. We might actually have a better handle on how to do this. But for now, I don't know. I'm a little bit nervous about trying to make decisions based on EMG data or a moment arm for overall outcome.
And with different exercises, I mean, I guess you could probably target different fiber sections or compartments of a muscle that maybe grow different regions of a muscle. I don't
very
know.
likely. Exactly. And we're still in our infancy of understanding, which exercise target which bits of a muscle. By the way, that might differ a lot between people who have different neural activation patterns, different moment arms, different architectures along the length of muscles. And this might mean that we can never just say this exercise does that. It might be that in a lot of people, it seems to do it. In other people, it's like this. And once you start to get those sort of things, the amount of research you have to do and the perfection of that research. And I think a lot of the people in doing the research, to be fair, they just don't have the tools, the detailed MR imaging or the ability to do multiple biopsies or whatever that would really answer these questions.
Yeah, and like you said, activation isn't everything, because I mean, look at the glutes. If activation was everything, we should expect them to see greater growth with the hip thrust than with the squat. But at the same time, the squat didn't really show much greater growth than the full activation. So there's probably something going on there. The overhead tricep extension study for Mayo, less activation overhead, but we saw greater growth. Although some people say it was pure edema, because how did the lateral and medial head grow along with the long head if they don't attach to the shoulder? So there's all that speculation going on.
Yeah, but the brain completely changes the action based on that. You can't just say a muscle is at slightly longer length and therefore this is what we expect, because everything changes, right? Everything changes. The way the muscles activate changes. Remembering that when muscles are working, there's lateral transmission between the muscles themselves. And there's lateral pressures placed by one muscle on another muscle. And if the extracellular, you were talking before about, I wonder if the extracellular matrix might have something to do with hypertrophy. Well, of course, if one muscle is placed at a much longer length, and therefore the way it behaves, the way the fibers rotate and elongate is different, it's going to create a different shear stimulus on the muscles nearby. And if you're right, then that would affect the hypertrophy of the muscle nearby. It just gets so complicated now that it's not just, long head of triceps was at longer length, what happens? It's just not, there is not a perfect model. And this is why people go down to animal models, which are imperfect for other reasons, because we might be able to take a muscle out of the body and train it in isolation to see actually what the effect is. Of course, you then put it back in the body and it's so complicated you no longer see it. But yeah, maybe hopefully your listeners are getting an understanding that we don't just say it's complicated because we don't know. And we think, well, clearly I'm really smart. So if I don't know, it must be because it's really complicated. It's complicated because we really do know how complicated it is. We know how muscles impose forces and shear stresses on nearby muscles. We know that muscles release exokines, myokines, that signal not only within their own tissues, but signal in a paracrine fashion, probably to the muscles, not only within the synergistic group, but even to the tendons. So we know that the way one muscle in a group works can then directly affect the next muscle simply through signaling processes, molecular chemical signaling processes. Then you've got shear stresses, which are affecting, that then transmit forces into the neighboring muscles. And so all of these are going to affect it. So when we say it's complicated, it's not because we don't just know, it's because we know how complicated it is. And that's why we get so scared to say anything, because we know that it's not as simple as, I put a muscle at a longer length, I should see something.
Yeah, and there could be many reasons. I mean, back with the hip thrust example, like maybe that higher activation was able to offset the longer length because maybe the glutes weren't stretched enough, or maybe there was less activation there,
in hip thrust, you're also, it's not just that in hip thrust you're working the glute. It's because you're flexing the knee, so you're putting the hamstring muscles, the biarticular hamstring muscles, at the shortest possible length, which means the way they shear across each other is completely different. And of course, your brain will, over time, not in the first day you ever do a hip thrust, but over time, the brain will have to learn that under those conditions, it's going to have to try to activate the glute, maybe preferentially to the hamstrings. And I know a lot of people watching this will go, oh, you can't just, if I couldn't activate my glute fully or couldn't walk up a stair. And I always say, yes, but I can do a push-up. Doesn't mean I can bench press 150 kilos, right? Activation is not just activation. So it could be that you eventually learn over time during hip thrust to activate the glute in a way that is increasing molecular signaling for that. But if you do squats all the time, you've now got a lot of force in hip extension, but you've also got the hamstrings. Maybe there are different amounts of different types of signaling that end up giving you about the same result. Yeah, but through different, we talked about the complexity of hypertrophy. You might end up with somewhere similar result, but through different mechanisms. And so until we can really partial them across, and until we get proper studies where we actually get well-trained people doing full training and then just adding a bit of hip thrust to it to see whether that over 6 months actually makes a difference, a detectable difference. I don't think until we can do those big studies, I don't think we'll truly know. I think there'll be a lot of speculation. So maybe we need some citizen science here. Anyone who is near any of these universities that have the ability to do it, maybe we can do some studies and combine all the data and actually see over 6 or 12 months what's going on.
And maybe the neuroactivation pathways for a squat can change with a trained lifter and probably be better for glutes.
Exactly. Very likely.
Dr. Blazevich, this podcast is a lot longer than usual, so everybody has a lot of information to take in, gives them a lot to think about. So I really thank you for your time, because I know this was a pretty long podcast, but the amount of information and your excitement when talking about these things, I think, brings a lot of people into wanting to learn more about it. And I'll link your Sarcomerogenesis paper at the bottom, maybe where people can find you. Are you on anything social media wise, or?
Yeah, it's not an easy place to be, is it? Yeah. I'm on Twitter, or it's now called X, at Tony Blazevich. I think Instagram, although I hardly ever use it, but I really shouldn't I? Because all the kiddies use it, is Tony Blazevich as well. And if you want to go to tonyblazevich.com, outside of my billion hours of work, I do try to put little things up there. So you might find some of them of interest. Even if you've got little kids, there's a kids page up there as well. So good luck with that.
If it's okay with you, I'll probably add them down in the comment section and the captions. But thank you again for your time. It was a really enjoyable podcast, a lot to think about. And I will see you guys on the next episode.
Perfect. Good to talk to you. Enjoy.